I sent you a message. I have sent you a message on LinkedIn with a invitation link to the live stream. Welcome, Ed.
Thought I'd get on here a little bit early just to make sure I know what the platform is like. But I see it's Google.
Yes, I'm using Google because I'm still getting a paid account, or how do you call it? Zoom.
Well, you could do Zoom from between now and Christmas because I think they're lifting the time limit over the holidays.
Oh, serious? Are they lifting the time limits?
Just over the holidays is my understanding.
Okay.
Now, I would want to test that first because I don't know when it starts and when it ends, but maybe you could look it up.
I've done this, and it ended after 6 hours. So Google has a streaming limit of 6 hours.
Wait, Zoom cut it off after how much?
Zoom cuts off after 45 minutes or an hour.
Yeah, 45 minutes is what I thought, unless you had a paid account or someone had a paid account.
So I'm thinking of Meg getting me a paid account.
Yeah, I have no idea how much that costs.
Okay, shall we test your camera?
Yeah, it's not on?
I'm not seeing it at the moment. Ah, yes, I'm seeing it now. Oh, there
Yeah,
you
it's
are.
on there.
Yes.
I see you and I see me in the upper corner.
Okay, perfect. Okay. Let's see. I can. Yes, perfect. So, yeah, we're a little bit early.
I know, and I tried to do that just so I could practice making sure I knew how to get on to how to
Yeah.
do. So some of these things are a little bit hard to do to both um, share screen and go full screen. If you know what I mean.
Yeah. I know, I know. Sharing is percent now in the right bottom if you like to share your screen.
Are you seeing it?
Let's see, let's see. No, not yet. Why not? Let's see. No, I see you, but not.
Interesting.
Hmm. Why isn't this?
I stopped.
Okay. Strange. Hmm.
Background borders. How about that? Can you see that?
Hey, now it's sharing. Yes, this is working.
How about now is that full screen?
Um, no, it's both. I see you as a little figure, and 90% is the rest. So the presentation is 90%, and you are very little in the corner, like showing, and that's perfect.
So like this is perfect.
Yeah.
That worked for me, but I can't guarantee I can stay in frame personally.
No, but it's okay. On your left, there is quite some light. Maybe you can turn the camera a little bit.
I happen to be in a corner of a room. So on my right, is this getting better or worse?
Worse.
How
Okay.
about this?
A little bit. Oh, this is better. Yes.
Right there?
Yeah, yeah. Even because there is otherwise a lot of light coming in from the windows.
Yeah,
So I'm
because
gonna.
there's a light on both sides.
Ah, yeah. But it's
Um,
okay.
that's why I'm positioned in the corner, and I'm back about as far as I can get with the hardware that's here.
I was trying to live stream the event, but somehow my live stream didn't want to connect to you to Google, to YouTube. So I'm just gonna record it and afterwards put it on the YouTube. But yeah.
Oh, so we're not going to be able to get questions?
Yeah, we're gonna get questions from the people who are joining directly into from the community that's joining in
Okay,
the chat app. So,
okay,
but normally I live stream it so I can manage it on two screens, one here and one there. Um,
yeah,
and then I see the YouTube stream with the questions, and I see the meetup itself.
okay,
But for some reason, my security key, which YouTube provides, does not want to go into the software today. So record it and then put it afterwards on YouTube.
okay.
Yeah, I don't know why, but it's. Let's see if James
So
is.
what I did that seemed to work was to present a window as opposed to present full screen.
Yeah, present a window is the.
But but then I went to full screen, which is basically the full window going full screen. So I didn't. So if I do entire screen, that's that. And you said you couldn't see that, right?
No, the window is the window frame without the Windows bar at the bottom and all the browser
Mm-hmm.
what you have open. So it preserves your privacy in that kind,
Mm-hmm.
and it doesn't show your complete window screen. It just
Oh,
the
okay.
content you clicked on.
Okay.
So that's a privacy preserving thing because a lot of people were complaining to Google. No, I need to make a distinction because there were like awkward URLs. Ah, the first visitors. Welcome, Dave.
Hello, thank you very much.
Welcome.
Thank you very much, Davy van Vieren here. I'm going to switch my camera off.
Okay, perfect.
Okay.
So yeah, we have a few more minutes. People will come in slowly.
Yeah. So what time do you? So you have it scheduled to start at 2. What time do you actually start typically?
Normally we start around the whole hour. People come in 5 over. We start with the guest and that kind of thing. So hey DM,
Okay.
welcome.
Yeah, Good day, Mr. Pheil. How are you?
Ah, very good. It's Pheil. Think German.
Deutsch.
I always tell everybody that the people that speak German get my name pronounced right the first time. Other than that, if they're English or any other language, nah.
You said, what did you say it was? Pheil?
Pheil.
Pheil.
As in pronounced F-I-L-E.
Pheil.
Pheil.
Now,
Pheil.
I'm
As in
Afrikaans.
file cabinet.
I'm Afrikaans, which is very close to German. I'm trying to fail. Yeah, that's probably what it is. Fail in Afrikaans. That's
Well,
interesting.
at least that's closer to most people. Most people are, the E comes first, though you pronounce it.
Mm.
Yeah. File. Feel. You will hear a lot of different versions of the same. Yeah.
Yeah. So over my history, about 10% of the people got it right the first time, and 90% got it wrong.
Okay. Okay.
I assume I go first since John's not on yet.
No, but I've sent him an email and I've sent him also a Telegram message. Let's see if he responded. Oh, he definitely got my mail.
Good. Is that because Telegram said you did?
No, because he responded.
Oh, okay.
Yeah, that's the most obvious cue. See, yes.
That's the secure cue. The fact that Telegram says he saw it doesn't necessarily hold water.
Ah,
Good.
hello, Chris.
That's because Telegram said you did.
Well,
Oh, okay. That's the secure cue. The fact that Telegram says he saw it doesn't necessarily hold water.
What's going on? Let's see.
Hallo Hulmo. Hallo
Hi.
Dion. Hallo David.
Hello, Chris.
Hoe gaan dit?
Goeienaand. Good evening. I'm switching my microphone off as well because I know that the internet gets overloaded. So, but I'm still here.
Perfect. Slowly people coming in. We're now at 6. Nice.
David, jy ken vir Dion seker, né? Of Dion, jy ken vir David.
Ek glo nie.
Dion, David is by Tikkies Chemiese Ingenieurswese. Ek het hom ge-invite. Dankie dat jy aanvaar het, David.
Oh, dankie vir die thanks for the invitation. I'm always curious.
I graduated at Tikkies in 2009. So were you there already, or that was 11 years ago?
I joined Tukkies in 2017, so you finished before I joined.
Well before, okay.
Ja, David is a lithium specialist. One of so on the metals side, molten metals and into thorium reactors, I think I can recommend David.
Oh, thank you very much, Chris. I can just say that I've got many scratches on my back.
Yeah, long as you don't get sodium in them or lithium.
Yeah.
Yeah, as the thorn bush is thick here in South Africa.
probably will be coming more people in, but 5 over is 5 over, and then we'll see, we'll just start.
David, if you can pass on your email address, I would appreciate it. Whether it's via Chris or over here is fine, but I'd like to have a chat with you, maybe even on Friday if you have time.
Okay. No problem. Chris has my email, but I'll look for yours and I'll send it to you directly as well.
It's
It's
Dion.
Diane. It's Dion. Okay.
Dion at thoriumnetwork.com.
Okay. I'll do so.
Cool.
Perfect. Okay, now I hope everyone is ready. Phil, I'm gonna close my camera and I'm gonna give you the floor.
Okay.
So,
Tell me when you're ready. I assume, can everyone see the presentation screen?
Not yet.
I see an angry thorium character.
you see an angry thorium character. Yeah, that's Thor, the angry god with his hammer. Okay, you maybe start presenting.
Can we see the my presentation slides now?
No, not yet.
Oh, are they lagging, or do I not have control?
I don't know yet. Somehow I see you, but I don't see the screen you're trying to share.
No. Oh, just a second. How about now?
Yes.
Are we good?
We're good.
Okay. So my name is Ed Pheil. I'm Chief Technology Officer of Elysium Industries, and we're developing a molten chloride salt fast reactor. And I'm going to overview our reactor and what it does at a fairly high level. I'm being a CTO and a technical person. If the technical review isn't over 4 hours, it's not a technical review. It's just high level.
Okay.
So a bit of my what was that? Oh, disclaimer. Yes. Yeah. So my background is I went to Penn State, got a degree in fusion, and I spent 34 years designing reactors for the U.S. Navy. That include their main water reactors. And I operated those reactors. I trained Navy students to operate those reactors. I started up new reactors. But I also worked on every type of reactor that you can imagine to see if there's a better alternative and to make sure we're aware of what the other countries might be coming up with. You can see there all the different types of reactors that I've worked on. You'll notice that not all of those are U.S. reactors. But there are CGNs, which are destroyers, or guided missile cruisers, sorry, and aircraft carriers. Lots of different submarines of all sizes and foreign submarines as well. New reactor startups. I started up Los Angeles class, Trident class, NR1, which is a deep diving baby submarine, and Virginia class submarine. And I was involved in the Columbia class design process. I was also involved for a couple of years. NASA contracted us to design a reactor to take a spacecraft to Jupiter's moons, Jupiter's icy moons, called Jupiter Icy Moon Orbiter. It's a Prometheus program. Oops. And that went on for a couple of years until a new president got into office and changed the priorities of the space program. And then NASA canceled it, which is a problem working with NASA. But it was a very fun design because the reactor was started up on orbit and flew to Jupiter's moons, and the reactor was had to operate 98% reliability of success for 12 years. So it was a very long-running reactor.
Is this the same reactors that is on the Mars rover?
The Mars rovers and stuff are just plutonium isotopes decaying, making heat, and converted to electricity. They're not reactors per se. They're just decay heat sources. All right, but Kilopower is talking about building a pure uranium metal fueled with heat pipe cooling, going to Stirling engines for power for scientists, astronauts, or whatever you want to call them on Mars, going there to stay. So 10 kilowatt reactors, 4 of them for about a 4 to 6 person team, which I also worked on that too, by the way.
Nice. So you're very long into the history of nuclear.
Yes, particularly focused on the naval nuclear, but considering the fact that we've looked at every type, that includes quite a lot of the commercial work as well.
Did you also experimental? Did you work on experimental phase things?
Most of the experimental stuff was associated with detection and reactor startup testing. Making sure that all the parameters were right on the reactor startup to get it started up safely. I was doing startup testing on 2 brand new reactors a year and 1 refueled reactor a year.
So quite busy.
That was a fraction of my time. But I had done it so many times that I didn't have a lot of preparation work. I trained other people to do it and go with me to help out. Yeah.
I know you did also some consultancy work for the International Atomic Energy Agency.
Yes, I did on safeguards type work with MSRs.
How did they approach you? Were you contracted, or did you apply?
I was contracted as a private contractor to do work for them and paid through Brookhaven National Lab to work on that the model for safeguard, particularly for MSRs, but also for accelerator-driven neutron sources and fusion neutron sources, and a few other types of neutron sources that they didn't have in their model yet.
Okay.
Oh.
Really, really nice. So there is you've got a lot of history. So how did you end up starting Elysium Industries?
I was at the naval reactors and I was bored out of my mind building water reactors. If you can get that way. I have built water reactors for 34 years, and I wasn't learning anymore. I like to learn. So I realized that the naval reactors was running out of experienced people, and I knew that the commercial industry was well out of experienced people for designing new reactors. So I decided to leave the employ of the Navy which is actually a contractor for the Navy, to help the commercial industries out to build advanced reactors and reactors that help solve a lot of the problems that people have with nuclear power. Right, and so we did a survey of all the different kinds of reactors, and what their economics were, and whether or not they would solve the problems that people were concerned about, and we ended up with a molten chloride salt fast reactor.
Why a fast reactor?
A fast reactor because it has the best neutronics for consuming the waste of other reactors. If I go to the next slide, under the fuel line there, you'll see that uranium-233 has 2.3 neutrons per fission. Sorry about the typo, there's a G in there. It should be F. And you need 2.1 neutrons per fission to do both fission and breeding the new fuel. So you only have about 0.2 neutrons for leakage, absorption in other materials, absorptions in fission products and stuff like that. So you have to have very low leakage and a very clean system to have any chance of closing the fuel cycle on that. And you can't use anything but the uranium-233 to do that. Uranium-235 isn't much better at 2.5 neutrons per fission, but plutonium, you end up at 3 neutrons per fission. So you have almost a full neutron extra to do with what you will. And what that allows you to do is it allows you to transmute fertile materials, even if it requires multiple transmuting to different things. So like Pu-240 might go to 241 and it might decay to americium, so you still have to add another neutron to get there. So it has the extra neutrons to be able to do that and close the fuel cycle. And the important part about it is it doesn't require you to eliminate all the fission products. So I don't need to have an online processing system to close the fuel cycle. One of the nice things about the fast reactor is the fission cross sections go down much more slowly than the fission product absorption cross sections. So the fission products are not nearly as much of a poison as they are in a thermal reactor. Therefore, you can leave them in the reactor and eliminate the need for online reprocessing or even frequent reprocessing. Like, so solid fuel fast reactors, the real reason why they can't leave the fuel in the reactor for a long time is because the solid fuel gets damaged. But the fission product buildup is also there, but they also have the cladding absorptions and damage to deal with. It's taking up some of the neutrons. We don't have the cladding absorptions, and the fission products are low, and we can't damage our fuel in the molten chloride. The chloride repairs itself about 5 orders of magnitude faster than the radiation damages it. So it's not damaged, so you don't have to replace it. The fuel never really goes bad.
So you can
it does
up all your waste. You can just keep adding waste until. So I suppose
we plan on
uranium or plutonium.
Well, we'll start it up with the intent is to start it up with spent nuclear fuel mixed with plutonium. So even if it's weapons grade plutonium, it's denatured by mixing it with the plutonium in the spent nuclear fuel, because that plutonium is 33% Pu-240, and the weapon stuff is 7% Pu-240. And you need to get it up to 10% to not be weapons grade. So you can do that. And then your fuel that you put into the reactor is not weapons grade.
No.
All right, so only the fuel processing facility, a production facility, is handling weapons grade plutonium if that's what you have. Otherwise it's not. So when we send fuel to our reactor, even for initial startup, it is not weapons grade fuel.
That's very favorable in the view of proliferation.
Very favorable, and that's one of the things we were trying to resolve is people's perceptions of proliferation concerns. Even light water reactors go through the first 2 to 6 months and stuff of new fuel being put in the core where it's weapons grade fuel, right? And that's why they lock it up for so long. Even can-do reactors, they lock it up. They make sure that it stays in the core for a year, so that they make sure they get out of the range of weapons grade fuel.
What is the volume of your reactor spent uranium wise?
How much spent uranium do we need to put in it?
Yes.
To start it up?
Yes.
That's about 70 tons of spent fuel and about 8 to 12 tons of plutonium, depending on which flavor of plutonium it is that you have. So about 80 tons total of actinides to start the reactor up. All right, so that sounds like a lot. All right, but don't forget, once the reactor is started, that if you start it up with the plutonium, that's the only fissile that you ever need to add to it. From then on, you're just adding spent fuel or depleted uranium waste or whatever that you have that's already mined.
I think you will have, your market here is not to generate electricity. Your market here is to get rid of spent fuel.
No, we have a dual revenue stream. Right, so one revenue stream is getting rid of spent fuel and getting rid of plutonium for countries that wish to do that, and there are a lot of them right now. And another revenue stream is either the process heat or the electricity that you generate. So one of the things that we're really interested in is the economics. And so having multiple revenue streams, both on the front end and the back end, are beneficial to improving the economics.
Wonderful.
So one of the other issues on the fuel is 90% of the cost of solid fuel is making of the solid fuel into fuel pins and fuel tubes and assemblies. All right, we eliminate that. So our fuel cost, or any MSR fuel cost, is about an order of magnitude less cost than a solid fuel reactor. So when you talk about a fast reactor and the economics, a fast reactor, you have to refuel and reprocess and remake new solid fuel about every 4 to 5 years, right? Which means you have a recurring piece of that cost of making solid fuel, plus you have an expensive reprocessing system to do that. We don't have a reprocessing system. We have a purification system that every 40 to 60 years we take the fuel out and we remove the short-lived fission products and leave the all actinides and the cesium and strontium in the core or in the fuel, and put it back in a reactor. What's that?
Can be created. How do you deal with gas creation?
We have which I don't have specifically in this presentation, but there's a system developed by MIT and Pacific Northwest National Lab that uses a metal-organic framework, and it uses different configurations of that. The first configuration of it pulls xenon out, and the second configuration pulls krypton out and allows argon to go through. So it's basically an argon purification recycling system. So it pulls those out and stores them in the metal organic framework, which is a low pressure system. So you don't have to have it super cooled, and you don't have to have a high pressure system for it. You would just swap out tanks after they got filled up. But the beauty of it is it recycles your argon, the cover gas on the system, and takes out those gases.
Would it be possible for a reactor design like this to get out medical isotopes?
It would, but that would require an online processing system to do it. Typically, medical isotopes are the short-lived ones, and we only take our fuel out every 40 to 60 years. So all the only the short-lived stuff that's been created in the last year really would be available in the removed fuel. So if you really wanted that, you would need to put an online system to pull those out and pull the medical isotopes out. It might actually be easier and more economic to put a cell in with the target material in it and be able to pull that out whenever you wish. One of the advantages of a molten chloride fast reactor is there is absolutely no structure in the core, and there's no structure around the outside of the vessel. Right, so you can put a cell anywhere you want. You don't have to design test cells and fuel around test cells to be able to generate the isotopes. So that's very viable to be able to do that. And that's probably less of an issue than trying to put a full stream reprocessing system to pull medical isotopes out. Now another point to be made on the medical isotopes is you only need about 2 or 3 reactors in the entire world to produce all the medical isotopes that you really need. All right, so you don't need to have a medical isotopes extraction system on every power reactor that you have. You need a lot more power than you need medical isotopes.
Yeah, definitely. But
So
it's still it is optional to to make them with the design.
yes, you could do that.
Okay. Why did you choose for chlorine and not other salts? Chlorine, I know chlorine is cheap, the chlorine-based salts. It's
The
most
chlorine
common.
doesn't require highly enriched lithium, which is expensive. Doesn't produce tritium. I can go to my grocery store and buy sodium chloride. I can buy potassium chloride. I can go to my pool store for swimming pools and buy calcium chloride. I can go to my highway department and buy and pick up magnesium chloride. So it's dirt common and dirt cheap. So that's a huge advantage. The other advantage over fluoride salts, which are the alternative, it has lower absorption cross section. The problem is the fluorine itself has a high inelastic scattering cross section in the fast spectrum. So in about the 200 keV to about 2 MeV, the fluorine scatters all the neutrons out and down into the intermediate spectrum.
Unfavorable situation.
Yeah, you need the fast neutrons to get those 3 neutrons per fission. If you don't have the 1 and 2 MeV fissioning going on, you don't get that high, that 3 neutrons per fission in there. And that comes from the plutonium, but it also comes from direct fission of U-238. And direct fission of U-238 gives you about 0.2 extra neutrons, so takes you from 2.8 to 3 neutrons per fission, but it also gives you a delayed neutron fraction that's significantly higher than that of plutonium alone. As a matter of fact, if you fission the 238, it's dominant in the delayed neutron fraction. All right, so from a control perspective, you're better off having that chlorine in there and getting into the fast spectrum than you are if you're trying to burn in a fluoride where all those fast neutrons are removed, because you have a very low delayed neutron fraction.
What I was wondering, they're modular. I see that there are like heat exchangers on the outside.
Yeah, so in the picture there, the silver dome in the middle is the reactor, right? That's just a cap over the top of the reactor vessel to keep oxygen off of the top of the reactor vessel, because if you don't, then you get air corrosion on the outside of the reactor vessel. All the other components, the high temperature portions, are submerged in that tank. There are 6 loops around. The blue that you see is a pipe and a pipe heat exchanger, and we have better pictures later. That is fuel salt to clean salt heat exchanger. That clean salt is identical to the fuel salt without the actinides and fission products and stuff. And it is higher pressure than the fuel salt. So that if you, or I should say, when you get a leak in that heat exchanger, you leak clean salt into the fuel salt, and you dilute the fuel salt and you shut the reactor down. All right, and then the outer ring then is basically a clean salt to a gas heat exchanger. Typically, what we talk about is a steam superheater, where you have saturated steam coming in to that heat exchanger and superheated steam going out. And you might ask, well, why not water? Well, this is a fast reactor. I don't want water close to it. If I have to seal the pipes going into it, I don't want water sitting in this heat exchanger and boiling to residual heat in the salt, creating a long pressure spike that I have to get rid of. Whereas if I put steam in there and I isolate the pipes going in, you're isolating steam, and there's not much mass in there to create a pressure spike in case there's a leak into the secondary salt. So I don't have to blow it down for near as long to get rid of the pressure. So it's a safety basis that's a gas heat exchanger. The other reason for making it basically a steam superheater only, not a boiler, is because then I can use it for nitrogen or CO2 or whatever other gas that I wish in there for process heat instead of steam for some of the higher temperatures.
So would it be possible to run a supercritical steam cycle?
I guess. I
think he's talking about Brayton.
You mean supercritical CO2?
Yeah, like
Not supercritical steam.
yeah, like putting instead of
Brayton cycle.
cycle in this. Would it be possible?
I'm getting mixed signals as to what it is. Are you talking about a supercritical steam cycle? Very high pressures and stuff like that? I would rather not, because the pressures are so extreme, and the delta P across that heat exchanger is very high, because the salt on the secondary side is essentially nothing in comparison. But supercritical CO2 is better because it's much lower pressure, still high pressure, and maybe similar to superheated steam, but not as high as supercritical steam in pressure. All right, could you do it? Yes, you could do it. But the heat exchanger design is going to be a lot more difficult.
So it's unfavorable design-wise.
Yeah, I just choose. So one of the issues here is, why do people go to higher efficiency systems like supercritical steam? Right? And the reason is because they want to save fuel cost, right? In a light water reactor, the fuel is about 1/3 of operating costs, right? Our fuel is an order of magnitude cheaper, so we're about 3% of operating costs. So you don't necessarily need to drive the cost of getting a very, very high efficiency if you're getting revenue out of burning waste and you're not saving any cost on fuel, like you are with a standard light water reactor or coal plant or steam or gas plant and stuff. That's all about saving fuel. And if you're 3% or less of your operating costs is fuel costs, you don't need to go to the high cost of the plant of putting high efficiency systems on it. You can go for lower efficiency and get simplicity and lower cost for doing that. So,
Hey, Ed, can I jump in?
Sure.
Yeah, I think maybe he's inferring to like a Brayton cycle, but can't you just have another heat exchanger and get the high pressure system away from the reactor? You can do whatever you want.
Yeah, you can put another loop in. It's going to cost more.
Yeah.
But like I said, those heat exchangers are gas heat exchangers. So you can run a gas and run a Brayton off of that directly. It doesn't necessarily have to be supercritical steam, but it could be supercritical CO2. It could be a nitrogen or a carbon dioxide normal Brayton cycle. Right. You don't have to go to something really sophisticated. I'm nervous about supercritical steam because it's somewhat developmental. Supercritical CO2 is very developmental. When I have a reactor, I want that supercritical CO2 system to last 2-3 years without maintenance. Nobody does that yet, and nobody does it at the powers that we're talking about going to.
No, it is a lot.
All right, so I'm not ready to go for a developmental power system in addition to a developmental reactor. I've seen that happen before. ML1, they had a nitrogen-cooled reactor and a nitrogen closed-cycle Brayton on it, and the program failed because the nitrogen turbine failed, not because the reactor failed.
So, keeping it simple is a much cheaper and more
Yes.
safer option than being very experimental.
Yes. I am not averse to going to that in the future, as I just don't think that's the first thing we're going to do.
I was wondering about the building of such a reactor. Can I put this inside, like, let's say, a harbor where I have a lot of industry that needs a lot of heat, like not even converting it to electricity, but just starting to deliver it as production heat?
Yes, definitely. That is designed for that. The fact that we have 6 loops on here, each loop can go to a different process heat use. But obviously you can buy the services of 1 loop, 2 loops, 3 loops, or all 6 loops for one industry if you can use that much power. We're talking about 3,000 megawatts of thermal of power at 750 C for the initial reactor, and eventually 1,000 C. The nice thing about this reactor is you can start off with just one of these cells, so 1 set of heat exchangers, and that's so if you use the large full-size heat exchanger, that's 500 megawatts thermal and 200 megawatts electric. But we also have 125 megawatt heat exchanger sets and stuff, which is 50 megawatts electric if you make electricity out of it. So there's 2 size heat exchanger sets, the 125 and the 500. But if you're going to 1,200 megawatts, you might as well start off with the 500 megawatts, and then just add heat exchanger sets.
Ed, can you help me out with scale? If we're doing a 500 megawatt system, how big is it? What are the dimensions? I need a little help on that.
What are the dimensions of what?
If we had a 500 megawatt thermal reactor as configured here in the drawing, how big is that? I mean, what are the dimensions? This thing, the size of a Costco, or is it the size of a Walgreens?
So I don't know how big those are, but the reactor vessel, the silver part in the middle, is a maximum of 4 meters in diameter at the flanges. All right, so that it's road shippable. All right, each of the different components are under 4 meters in one direction, so that they're road shippable. The overall hexagonal flat is 19 meters in the tank that everything's submerged in, and on the corners is 21 meters across the points.
Beautiful.
That's actually quite such a large amount of energy production.
Well, the nice thing about it is the reactor vessel size is the same, regardless of how much power you're pulling out of it.
You're
right?
cycling it through faster.
That's exactly right. If you add a loop, you're doubling the amount. If you have 1 loop and you add a second loop, you're doubling the amount of flow through the core. The nice thing about this is most reactors are designed with excess reactivity in them. This reactor is designed with just enough reactivity to get critical, and that's it. And then you add fertile throughout the day. So add about a kilogram per shift through the day, assuming 3 shifts per day, about 3 kilograms per day for a full 1,200 megawatt, 3,000 megawatts thermal. All right,
He's
so
shoveling coal.
you're barely critical all the time. Yeah, we're talking about, you know, maybe something the size of a softball, no bigger than a football. You guys is football, not ours. But the size of the football is more defined by the carrier salt that's in with it as well to maintain the chemistry or the chemical composition. All right, it's not just the actinides. You can put just actinides in if you need to adjust the relative ratios. But typically the fuel added will include carrier salt as well. And you just drop it in as a solid in a flow path in the drain tank down below, and it'll dissolve out.
Do you have a full scale unit running yet?
No, we don't. It's still developmental. Still looking for funding to be able to do that. We're looking at building a prototype or demonstration unit 2027, 2028. In the United States, the NRC requires that to be under 10 megawatts thermal. So that 125 megawatt thermal heat exchanger, the reason why I have it in there is 125 and with a /10 on the front is they require us to be under 10 megawatts thermal. So I plan to put in 125 megawatt thermal and operate it at 10, and then ask for an uprate without any changes to the system.
So is that regulatory smart?
Please don't ask me if the regulators are smart.
No, it's like no. Never mind. That's a strange question.
Ed, I have a kind of a tough question for you.
Good, those are the best kind.
Okay, metallurgy, neutron bombardment, corrosion, life of core. I mean, to me, that's always a big issue. So where are you at in terms of metallurgy, long-lived metallurgy for this system?
We don't have long-lived metallurgy for this system. All right, we build this system modularly. And like, for instance, the lower half of the vessel is designed to be replaced periodically. The core lasts basically forever, or at least 40 to 60 years. But the lower portion of the reactor vessel is designed to be replaced
what you were upset about.
as it gets high damage rates. And the damage rates are, yeah, it's going to be a little bit of the D*T, but it's also going to be helium generation.
So what do you think for the lower part of the core? Are you going to get 10 years or is this going to be swapped out pretty regular?
Are you upset about?
It's probably going to be 15 to 30 years for the lower portion of the vessel.
Okay, maybe.
There's a little bit. So one of the points that I didn't really get to yet is that T cold is 600 to 650 C. All right, 316 stainless steel annealing point is 650 C. So displacement damaged is annealed out by maintaining the lower reactor vessel at its annealing point using T cold of the reactor. So all parts of the reactor are cooled by T cold, right? And that's the self-annealing temperature, i.e. the atoms that are knocked out of place by displacement by neutrons and stuff are a little bit more mobile such that they can move back into their place without getting so hot that you damage the crystal structure of the metal.
Why chose for this?
Excellent.
I'm sorry, I missed that. There's an echo.
Why did you choose this kind of metal? And I think this one is already certified.
It is.
Did you take?
You hit the nail on the head. This one's already certified.
Because it's one I know, then it must be certified.
316 is very common. So not only is it certified for nuclear, it's also dirt common. So all my supply chain and stuff, everybody knows how to work with it.
I was wondering about supply chain of your fuel. You would be an endpoint. So people could actually, um, you would either buy or people would even pay for disposal in your reactor.
Yeah, the goal is to actually have the United States is building consolidated interim storage facilities and stuff for the fuel from reactors that where the entire plant was shut down. Right, so the intent is to build a startup fuel production facility near those to access that stored nuclear fuel, and it also happens to be near the plutonium in the United States. So build startup fuel there, but the intent is to build the reactors at existing nuclear sites and then convert the existing spent nuclear fuel on those sites directly into fuel for the reactors without transport. And feed it in the reactor. And you can build a pretty compact system if you only need to convert about 3 kilograms a day, about 1 ton a year. So that system can be very small and operate very slowly and still meet the fuel needs.
That's perfect. I'm looking at the clock. I was wondering.
We're on slide 2.
I was wondering if there were any questions about this slide from the audience.
If I may ask a question, David van Vuren here, Ed. I don't know much about nuclear energy, but what I do know is about these corrosion caused by chlorides and molten chloride salts. And coming to the question of Jim Kennedy, my concern would be about using 316 together with the molten chloride salts at elevated temperatures.
You have to be careful when people say chloride salts and corrosion and stuff. They're usually talking about mixtures of salt, chloride salts, and water or air. Right? Yes, those are extremely corrosive, but pure chloride salts without air or water in them are less corrosive than the hot water of light water reactors. All right, and chloride salts are less corrosive than fluoride salts because the oxidation strength is lower. So they're not going to be as corrosive. Argonne National Lab has samples of chloride salts that they put in vats and maintained hot at 500 C for going on 34 years now. They took the corrosion coupons out because they could not measure any corrosion on them. Right? And they're maintaining the pots and they're still not getting corrosion on the pots themselves. So the thought that chloride is corrosive, that's associated with people's familiarity with a water plant getting chlorine in it. The issue is chlorine with water is bad, water in chlorine is bad, but pure water and pure chlorides and stuff are not corrosive. It's just a matter of keeping them clean.
I hear what you say, and I've used the same arguments, but that's where some of the scars on my back came from. I have corrosion and all sorts of funny things happening. We had to use very low carbon. We had to use carbide stabilizers. I think we had to go to 347 stainless steel, which in South Africa is almost impossible to get.
Yeah, I'm not averse to going to other steels and stuff that are already qualified. I am averse to going to a new steel like Hastelloy that's not qualified yet.
Okay.
All right, and the other alternative, and this is the method being applied by Terrestrial Energy and Thorcon is, okay, if it corrodes, I'll replace it more frequently. They're replacing the vessel every 7 or 8 years. and that's in a fluoride salt, which is more corrosive than a chloride salt. So there are ways around it, and that's one of the advantages of using an existing, very well-known steel, is that it's cheap to make the replacements. Whereas if you go to Hastelloy and you have to make replacements regularly, that's a lot more expensive because it's like, special made.
Shall we go to the next slide?
Sure. All right, this we've kind of touched on to some extent. The 316 stainless steel, the first generation reactor, the T-hot is 750C and T-cold is 650C is the intent, depending on what country it's in. Some countries aren't familiar with 650C operation. They're only familiar with up to 550C because they've only worked on sodium reactors for stainless steel. So you might have to go to 550C. That's causing us to relook at what our salt composition is to get our melting points down low enough to be able to support enough margin to 550C. So we're having to add, originally we were just going with sodium chloride, potassium chloride, uranium chloride, plutonium chloride. Oops, sorry. But if you want to try to get down to an operating point of 550C, you need a melting point well below 500C. Because because the highest risk event is freezing, and the most likely place to freeze is in the heat exchanger. It is very difficult to thaw a heat exchanger without cracking it. You can do it, but it's really, really hard and really slow. So that's where we're going for. You'll notice in the second generation, we're intending to go to 950C and 1000C, but T-cold is still 650C, all right? That's for the annealing, and that's because the materials that we have today are only qualified up to 650C. Hastelloy maybe 700C, but that's not much better. That gives us a higher delta T in operations until we get new materials that are higher temperature capability. So the primary salt is the chloride fuel salt, actinides, and low initial fission products, which is the low initial fission products is the 4% out of the light water reactor, because in our fuel production, we do not remove fission products except for the gases and the noble metals. So that might remove maybe not even 1% out of the 4% of the fission products, but it all goes straight in. And the reason for that is if we don't separate the uranium and the plutonium, the minor actinides and the fission products actively, it is not considered reprocessing, right? Because all the protecting mechanisms for the plutonium are still there, the uranium and the fission products, especially the long-lived cesium and strontium. They're all in there. So that's a proliferation benefit to not separate those. The second reason for that is I don't really care about 3% fission products from a light water reactor if I'm taking it to 40% fission products because it's a fast reactor. So 3% is nothing in the operations. So we can deal with that. The secondary salt is just a little bit lower temperature sets because you have a delta T across the heat exchangers. One of the things you can kind of see it in the heat exchangers, we are not using microchannel heat exchangers. All right, the reason is because the noble metal fission products tend to plate out on nickel surfaces that are cooled. All right, the heat exchangers are the first system that it goes to where the noble metals are going to plate out and it's going to clog them. So you want something that's not microchannel, because those microchannels, as soon as you clog one of the channels, that whole channel is gone. You want something that can get around local clogs and is shall we say, less tiny, less easily clogged.
Are those plates, or how am I envisioning this?
So it's a tube and shell heat exchanger straight through. All right, so no U-bend and stuff, but the tubes are twisted tubes to allow higher flow rate, higher surface area, and minimize the fuel volume in the heat exchanger. Don't forget, you still have to minimize fuel volume in the heat exchanger because of cost, because of delayed neutrons, and because of criticality of the heat exchanger. You need to make sure there's not too much fuel in there. So.
If the noble metals will to some degree also stick to such a surface?
Yes, that's what I said, and they will clog them.
So this is a much safer option and a much longer lasting.
Yes, I don't want to have to replace the heat exchangers because they're more expensive than the lower reactor vessel because there's more pieces to it.
Design-wise, it must be a very, very intricate but also quite delicate device.
The heat exchanger?
Yeah, like it
No,
need a lot of
it's not. It's not straight tubes where you need an interstitial support plates and stuff like that with a high density salt and stuff. That would be a pain to design for. These are twisted tubes. So if you're familiar with any of the twisted tube heat exchanger designs, the twisted tubes are such that the tubes actually touch one another, like every 10 to 20 centimeters along its length. And then you just put a strap around the outside to hold them in. And when you heat it up, they expand and touch each other, and they hold each other in plate without a support plate. So you just you create the twist rate such that they touch every once in a while, so that they hold each other in place.
And as they start working and heat up, they expand and become tighter together. Oh, so
Yes. We didn't invite it. This is a Russian Russian design, probably used in the Alpha submarines. But the Russians used this twisted tube heat exchanger type concept many decades ago. Lightbridge is developing this fuel for backfit into light water reactors, but they're not putting it in contact yet. They're just trying to backfit into the existing fuel systems because of the high heat transfer rate and lower flow delta P through the tubes.
and your secondary salt to steam exchanger, how is this one built?
That's basically going to have to be a straight tube because you have a high delta P from the whatever the gas is, whether it's steam or nitrogen or what, to the salt side. So you need something that can hold the pressure. So that's going to be a round tube to hold that. Although technically, theoretically, you could use a plate heat exchanger for that. I've just never heard of anybody doing much in the way of liquid to gas plate heat exchangers because the volume ratios are different of the two for the volume ratios for the heat capacity of the two. The pressure drop would be extremely high if you had pushed gas through the same size gap as you were pushing salt through to transfer the heat. So those are likely to be straight tubes going through. In this picture, you can't really see it, but you'll notice that there's only one pipe going from the reactor vessel to the salt heat exchanger, and one pipe going from the salt heat exchanger to the gas heat exchanger. Those are pipes in a pipe, so that the hot fluid is on the inside. It's not a containment boundary because the metals are not qualified as containment boundaries at the temperatures of 750 C, right? But the outer walls are cooled by T cold, and those are the 650 C, and those are the containment boundaries for those. The other advantage of having a pipe in a pipe is the hot pipe can just be a slip fit. It doesn't have to be sealed because if it leaks, you're just leaking it out into the cold salt, or actually leaking the cold salt into the hot salt. That's an efficiency loss, but it's not a casualty or anything like that. But that's why they're pipe in a pipe. Another advantage is thermal expansion. right? If you have two pipes attached to it, one is hot and one is cold, they're going to grow differently. And so, and the temperatures that we're talking about, going from room temperature to hot temperatures, that's a significant difference. And so having only the cold pipe being the limiting part, you only have 1 point of growth in there. So you don't stress the other pipe for that. And what you don't see is there's a skirt that attaches to the top of the tank, supporting each of these pieces. And the reason it's attached to the top of the tank, well, because they're modular and you want to be able to replace them. So you need to have the attachment points to lift it at the top for remote access.
The pumps, how frequently would you need to service them? And what kind of pump would you use for a liquid salt? Because salts at its temperature are not really viscous. They're very liquid.
Yep, they are. Right at this point, the only the pumps that I know of that have been built are centripetal pumps with long shafts, and long shafts for two reasons. But mostly because you need a shield between the motor and the impeller. The impeller can take the temperatures and the radiation. The radiation levels that we're talking about are so high that insulation becomes a conductor at these radiation levels. All right, so you need a shielding in between it, between the motor and the salt, to protect it. So you need a long shaft for that reason.
So
But also the temperature.
So mostly to shield the engine. Okay.
Yep, shield the motor. But I also have a different pump design. It requires no electricity and no moving parts. It requires special requirements on the coolant salt, though, to make it work, and it hasn't been tested. And I don't want to put that out as my first one because I would blow the minds of the regulators because they would think it's magic. But I know it works. It works with water. It works with oil already. It's in common use. So I just would need to figure out how to get it work with salt and then get the regulators familiar with it. But that's why I'm not using it first. But it gives a huge advantage if you don't have to protect an electric motor.
That's definitely a very Gen 2 or even a future prospect. That's definitely not the first choice.
Yeah, and you don't have to put the motor at the top either. If the pump has no moving parts and no electricity, you can put it anywhere you want in the loop. So it makes it a lot better. I was looking at putting it inside the reactor vessel. So,
Very interesting.
so the piece at the bottom is the drain tank. All right, so most people have freeze seals between the bottom of the reactor vessel and the drain tank. You'll notice that we do not have those. The tall vertical green lines are very long shafted salt pumps. Those pump salt out of the drain tank and up into the two vertical portions in the bottom of the reactor vessel. So they fill the reactor vessel, then they fill the heat exchangers, and then the green line on the heat exchangers is the drain line for the heat exchangers. So that, and then once you get the heat exchanger filled up, you start the main pumps, and they pull from an internal line through the green vertical on the bottom of the heat exchanger salt into the heat exchanger, and then there's an overflow line at the top above the impeller that allows excess salt to overflow back through the heat exchangers down into the drain tank, so that you're constantly circulating salt into the reactor and out of the drain tank and back again, right? And so that when either those fill pumps or the main coolant pumps shut off, the reactor starts draining immediately. I don't have to wait for a freeze seal. I don't have to figure out whether or not a freeze seal is going to work, how long it's going to work, whether or not it's going to melt completely. It is immediate drain, right? Which is a lot faster response than you can guarantee with a freeze seal. All right, this is a much simpler method. I know Oak Ridge National Lab has basically told everybody in the United States that the workshop, the molten salt workshop, you guys should look at this method instead of trying to do free seals, because it's much simpler. All right, so they support this method.
The drain tank, it radiates heat. If everything goes into the drain tank, how would you get it heated up again to start it up again?
Everything has heaters that are lined, all the major components and pipes and the drain tanks, and that they would be used to heat those components. And then there's the argon gas is internal. That cover gas, when everything is empty, would circulate throughout the reactor to equalize the temperature on the inside through internal components and thick components to make sure everything is hot, so that if you start pumping fuel salt in, that it doesn't freeze when it contacts a cold spot.
Yes, because that was what I was wondering. How would you get the heat exchanger started up from a cold situation? Because then salt comes in, it clogs directly. So you
due to freezing. Yeah, but all these things are also immersed in a salt tank. So this picture doesn't show it, but like this picture, that purple tank there is filled with clean salt, right? That salt is also heated, right? So these components are exterior heated, or when they're operating and stuff, they're exterior cooled. This is one of the things that keeps our temperatures of the metals down around 650 C, is because they're cooled on the inside by T-cold and cooled on the outside by this salt tank. But when you're trying to start the plant up, that salt tank is also heated. But don't forget, the fission products in the tank, in the drain tank, they also help prevent freezing.
Yeah.
It's not like a water reactor where you're worried about boiling it. You're worried about there not being enough fission products to prevent freezing.
It's the other way around.
Yeah, you got to turn your head upside down.
Then this is gonna be a fun one for the regulator.
Yeah, well, this is we already talked to the French regulator on this. They were ecstatic when we showed them our drain system.
Yeah.
And they asked if they could make this an international standard. And we said, well, we're not in control of that. They don't like free seals, in other words.
Yeah,
IRSN.
the seals. Okay.
Yeah, so.
Are there any questions from the audience about the materials and the Gen 1 and 2 of this design?
Or future.
Or future.
I didn't really go over that. I got to wait for the materials people to work on the future, though.
The questions that I have, I don't think Ed would like to answer, because I'm very curious about that fancy pump that doesn't have moving parts, and I'm very curious about the seal.
The seal on what? On the fancy pump?
No, the fast draining seal that you said instead of a freeze seal.
I don't have a freeze seal. I just the everything in the reactor and the heat exchangers is constantly draining to the drain tank. The only reason I can keep the reactor running is because I keep pumping it out of the drain tank back into the reactor.
Okay, so you don't have a valve in between.
No. I hate valves.
Yeah.
First rule of power system design: valves leak. Second rule: heat exchangers leak eventually. You have to assume those are going to happen. And with salt, it's real hard to guarantee that that's not going to happen real fast. Yes. I don't like valves. Salt valves. Gas valves are fine.
Yeah.
So no free seals, no seals, no valves.
Yeah, the only valves that I found with molten salts that works, but it's slow, is to use a freeze valve. But yes, then you need a cooling device and the heating device on the valve.
Yep. And the problem is they're assuming that some of those freeze valves are part of the safety case.
Yes.
And guaranteeing how long it takes to melt and establish full flow is extremely difficult, especially as the plant ages and gets impurities in it. So I'm just avoiding that. I've built many reactors in my lifetime. I try to avoid things that cause me headaches.
And your molten salt pump, what do you use there? Positive replacement?
It's a centripetal pump. This one is.
Centrifugal.
Yep. Oh. Initially, because that's what's been designed for molten salt in the past. So there's experience doing that. That's why that's going to be the first pump. The second pump will be that magic pump that has no moving parts and no electricity.
Is that a secret still?
Sort of. You can look up on fisonic.us, fisonic.us, and they have one where they're using for pumping water, but it's also used for pumping oil and stuff like that. But that company that I mentioned, Fisonic, is they just do water. Although they're talking about doing ammonia too for air conditioning, because they're a building heating company, basically. So building heating and air conditioning type stuff. That's the only place in the United States that I know is using that pump. All the rest of them are in Russia. And so I can't go there because of my history with the Navy.
We can offer off.
Okay, we ready to move on?
Yes. And anyone other questions?
Okay. So this is just an example of the how you can be flexible power. So the reactor is the same one in all these pictures. The first one is essentially either a small 125 megawatt thermal or 500 megawatt thermal set of heat exchangers. And it's just got the reactor, one heat exchanger for salt to salt, and one heat exchanger for salt to whatever the process heat or steam for a power system or whatever the power system is. All right. And then you would add, just as you needed more power, you would add another 500 megawatt heat exchanger to get to 400 megawatts electric, and then add another one and another one that gets you to 800 megawatts for 4, and the 1200 megawatts electric for all 6 of them in there. The heat exchangers are in the thin direction, which is supposed to be under 4 meters, are not 4 meters. So we have room to grow. So you could theoretically do, if you wanted to only do process heat, you could do 5,000 fairly easily. The reason for the 1200 megawatts electric is to minimize, is a grid determination, not a reactor determination. And that's so you don't lose more than 1200 megawatts electric, so you don't have to replace 1200 megawatts electric for backup power, right? If you get much higher above that, it's getting difficult to come up with backup power.
In case you find yourself in a 400 megawatt electric facility, and it's been decided that it's not enough. Can you add in a simple
Yes.
way, or is it more difficult? And do you have to completely stop, drain, make every, or is it like stop, just put the module in, connect, and start up again?
Well, you'll notice that there are blank flanges on the outside of the reactor vessel for connecting the other loops on that 400 megawatt electric version, right? Or even the smaller one, right? So the intent would be to drain the fuel salt into the drain tanks and drop in another heat exchanger set, attach it to the vessel, attach it to the outer heat exchanger, And then you'll end up having to add more fuel salt for it when you add the additional heat exchanger. But yes, then pump the fuel salt back in and start it back up. Well, heat it up and then pump it back in. So yeah, the intent is that you could modularly increase it as you needed without replacing the reactor itself. You just add heat exchanger sets and turbine sets, as the case may be.
Perfect. So it's quite a lot of power coming from such a small device. The intensity of um, thermal energy generated in relatively small vessel is quite high.
Yes,
Mm,
that's because the fuel can't be damaged. There's no heat exchanger inside the reactor vessel to be damaged, so there's no solid structure inside the reactor vessel to be damaged, and the fuel can't be damaged because it's self-repairing. So you don't have to change the reactor size.
so it's purely replacing the vessel only once every 45 to 60 years?
No, probably 15 to 30 years.
15 to 30 years, okay.
The lower vessel, not the upper vessel.
The lower vessel. Okay.
All right, and the reason for that is, and this is something that people aren't really aware of on molten salts, is if you put a reflect. So most reactors, fast reactors and whatnot, the fuel stays in the core region, and you put a reflector around it. Well, that reflector around the core is also a shield for the vessel. Right? But if you have a molten salt reactor, even if you put what is called a reflector around it, right, that reflector is still going to be cooled by molten salt. And outside of that reflector, the downcomer going down to the bottom of the core region and stuff is still going to be fuel salt. Right? So any fuel salt that's going through the reflector cooling it is also going to be fissioning, and it's more thermalized out there. So you're going to get higher power peaks from fissioning, and it's not going to be very effective at attenuating neutrons because you're creating new neutrons in the fuel salt that is cooling the reflector and outside of the reflector. So the effectiveness at shielding the vessel is poor for a reflector. And that's why we just got rid of the reflector out of the reactor vessel altogether, because then we don't have to deal with contamination and cleanup of that reflector in the small tubes for cooling it. In addition to trying to figure out how to get it cool, even though you're fissioning within the reflector. Because, I don't know, most people don't consider steel being a moderator, but I consider all material being a moderator. If it slows down neutrons that are 12 MeV down to 1 or 2 MeV, then it's moderating the high energy neutrons down to a fast neutron, or what we call a fast neutron. So it is moderating, it's just not going down to thermal.
Yeah, in that case, every substance in the known universe is a moderator.
Yeah, and the best neutron absorber in the world is a vacuum in space.
Definitely. Were there any questions from the audience regarding the flexibility of power?
All right. Fuel cycle. All right, this is our preferred fuel cycle. All right, on the left, you see a light water fuel cell or a CANDU fuel cell. You take those and you chop them up into like 2 centimeter lengths. That's a mechanical process, and you split them lengthwise to help get the fuel meat out. Depending on the burn up, it may be powder, it may be chunks in there, so you may need to split it to get it out. And then you pour that in. So then you have a vat of the molten salt, the carrier salt, with one extra component in it, which I'm going to keep that as proprietary. All right, which that other salt steals the oxygen out of the uranium oxide and the plutonium oxide and fission product oxides that are in there, right? So the oxides then are precipitates. They're solids that precipitate out, right? But they're micro precipitates, so you actually have to filter them out, right? But the oxygen goes away, and everything in there becomes a chloride, except the noble metals and the noble gases and the zirconium cladding of the old fuel pins, right? And the cladding falls to the bottom, and that's filtered out with the noble metals. The gases are off-gassed and collected using that metal organic framework process that I talked about, but in this case, lower temperature operation. You don't have to cool it because it's already really cold. The gases are. And then once you've got all this spent nuclear fuel in that you need in there for the fuel, you add the plutonium metal or plutonium oxide, and the same thing happens. So you add your fissile last, and the reason for that is because your spent nuclear fuel is your poison. It's uranium-238, plutonium-240, and fission products are your poison to suppress the reactivity of the plutonium that you're adding. And you're diluting the plutonium so that you're going to a safer condition, and you're denaturing the plutonium in the process. All right. From that, you go ahead.
Be classified as weapons grade because you get weapons grade in and downgrade it during the process. So
correct. So it's not weapons grade once you've mixed it with the spent nuclear fuel. We're doing about a 10-to-1. So a 10-to-1 is about what you need to get to from weapons grade to well below weapons grade. So and 10% is about what the fissile that you need in the reactor. If you're putting weapons grade in, it's about 10%. So that works out just perfectly. If it's not weapons grade, then you're not going to put 10% in because you're actually going to put more than 10% in because only 2/3 of the reactor grade plutonium from light water reactors, if it's already separated reactor fuel plutonium, is 2/3 of it is 239. So 1/3 is 240. So you have to add extra plutonium content to get your fissile up to 10%. So you got to focus on what is the fissile content. You need about 10%.
How do you get the precipitation at the bottom out?
Just filter it. That's certainly some of the noble metals are, the zirconium. They're large. They're easy to filter. And then you would use a nickel, like a nickel mesh filter to grab the noble metals. And the oxides are going to be particulates. That's just a mechanical filtering of smaller size. I mean, you might even think about centrifuging it to get the particulates to go out the outside, just like a simple oil filter to separate out metals out of the oil. Same thing. There's lots of known processes already to do that. All right, and at that point, if you did your chemistry right and your ratios right and stuff, it's ready to pour into the reactor and start the reactor up. You heat the drain tanks and you put it in the drain tanks.
That sounds so
yes.
much cheaper and easier to do than what we're doing right now.
Yeah, cheaper and easier than solid fuels. That's why it's an order of magnitude cheaper than making solid fuels.
Yes.
I don't have any tight tolerance tubes and tight tolerance fuel pellets and tight tolerances on straightness, and the fuel assembly assembles, and differences in fuel enrichment in different areas to track. Everything is identical in enrichment, so I don't have to worry about what goes where. So we get rid of proliferation concerns. It's non-weapons grade before it goes in any reactor anywhere. We get credit for getting rid of weapons material. We get credit for getting rid of plutonium. Like France has a lot, and UK has a lot. United States only has weapons, so we get rid of weapons here, including SS stuff that they should allow us to have. Japan has, I think, maybe 20 some tons of plutonium, much of which they would like to get rid of because they're not getting their MOX plants back up very fast. So they're looking at ways of getting rid of it.
Is that why there is Japanese with a little star beneath it?
That's associated with the process for stealing the oxygen. It's a Japanese process, so it's not a US process. Funny story is we've tested this ability to extract oxygen with this process at our national lab, and they they marked the report no foreign. We can't export it. We can't tell foreign nationals. I said, well, that doesn't make any sense because the process is Japanese. How can you possibly stamp it no foreign? But I don't make the rules. But I can't tell you what that process is, in other words, because the government says I'm not allowed to, even though it's a Japanese process.
Oh, there's a question.
Yep.
Let's see. If you would like to read it out loud, then the other people also know what the question is.
Are you going to read it or me? I don't see any questions.
It popped up, but I don't know where it is now.
I'll ask quickly. What happens if you add water to your hot salt? Because I've seen a video where molten sodium chloride explodes when it gets introduced into a fish tank full of water on YouTube. Now I don't know how accurate that is, but I do have to ask.
That's accurate. So the sodium process is everybody's familiar with. You drop sodium in, you get a triple reaction. You get all the electrons running off of the sodium into the water, which causes only the protons to be left in a positive charge. So you get a Coulombic explosion, creating a porcupine explosion, which massively increases the surface area by orders of magnitude, which then allows the sodium water reaction to occur to create hydrogen, making a hydrogen generation explosion, and then the hydrogen comes off the top, making a hydrogen explosion in air. So it's a triple explosion process. In molten salt, right, that you don't have the mobility of electrons because the ionic at the temperatures that we're operating at. But that process that you saw the video on was up in the very, very high temperature molten chloride salt, sodium chloride salt, right? In the, say, maybe 1100 to 1300 C range that they did that. And in that case, the electrons are a lot more mobile. And so I think you still get the Coulombic explosion occurring there, but you don't get the hydrogen generation explosion. You don't get the hydrogen explosion after that, but you do get the Coulombic explosion from that. But we're not putting water in the reactor or letting water anywhere close to the reactor. The bigger concern is not that explosion, which would be well contained in small volume. It's more if you put water in the fuel, that's a moderator. All right, and then you become a thermal reactor with fast reactor fissile densities. That's a problem.
That doesn't play well.
That's why that heat exchanger out there is a steam to steam at most, and is not a steam generator. Is to keep that water away from the reactor, and it is two loops. It is two barriers away, even as steam. It's 3 baries away when it's water. There's another, I mean, the water is boiled outside of containment.
Hey, Ed, can you hear me okay?
Sure.
Yeah, I think what Dion Kemp was asking, what happens if you inject a slug of liquid water into very hot molten salt? You know, of course, you'll just get a steam explosion, but furthermore, molten chlorides.
Yeah, unless it's extremely high temp. He was talking about a video that he saw online of sodium chloride exploding in water, and that was extremely high temperatures.
Yeah,
that was not a steam explosion, because when you throw a lump of sodium chloride into a vat of water, you don't have enough surface area to create that steam explosion like that. So that explosion had to be Coulombic.
Right. Well, also, I think you were thinking about elemental sodium instead of a stable chloride compound, but
correct.
Still at high above several hundred degrees, thermodynamically, steam and molten chlorides will switch around to hydrogen chloride and metal oxides. You know, so
yes.
We don't want that.
Yes. Yeah. You never want water and salts together. Everybody has a car that it corrodes because salt and water get together, let alone steam and water.
We have to worry about tritium chloride forming in the bath, or tritium elemental tritium forming in the bath?
We don't. The only tritium that we get is the tertiary fission product tritium. So very low
pretty
concentration.
Once in a blue moon, right?
Yeah. Yeah, very low fission fraction. I actually have my chart of the nuclides here. I carry it with me everywhere.
I bet.
Actually, they don't give the fission fraction for tritium. Oh well. I'd have to look it up in a book. But yeah, keep the water out. That's true of any fast reactor. Usually the sodium water reactions that people are concerned about, they're not actually sodium water reactions. They're typically sodium concrete reactions when it spills out of the secondary sodium loops, not the primary loops, because the primary loops are all, you know, an integral reactor, and so very hard to leak primary sodium. It's the secondary sodium that leaks out.
If I can just ask a second bit on that question. Last time on this meetup, I was presenting, and Hulmo asked me about taking molten salt reactors, fluoride salt reactors, onto submarines. I've heard rumors of that happening in the world. And then if you get water that goes into those reactors, that's kind of more or less what I'm concerned about. What will happen if you put a molten salt thermal reactor into a submarine? It gets flooded with seawater. What will happen with the?
You mean you sink the submarine?
Yeah, or something like that. Or it's on a boat, and something.
It's just gonna. I mean, you still have your multiple barriers to release. As far as I know, most of the submarines that are out there, when they sank, they didn't lose their fuel cladding containment barriers. Now you would in a molten salt reactor due to the high pressure of the ocean. Crushing things probably, unless you design for that. But water getting in, I mean, certainly the fluoride salts are non-soluble, or at least the lithium fluoride, beryllium fluorides are non-soluble in water, but in general, they're going to eventually corrode away. Like you said, hydrogen fluoride and hydrogen chloride are going to break them apart. All right, so yes, it would be released to the water if you did it in a submarine and lost it.
Thank you.
But I mean, that can be engineered around easy enough.
Any other questions?
Here's just a closer up picture of that one that I saw that you can see the flow paths. This region here, from this point down to the bottom head, that is the core where you have enough critical mass to go critical. All right, notice it's semi-spherical, a little bit cylindrical in there. The flow goes out this center part up the top and splits up to 6 ways into the inside pipe of the pipe in a pipe, goes into the heat exchangers, goes in the top, goes down the outside of the tubes, flows into the central riser pipe, goes up into the fuel pump, is discharge goes down along the outside of the shell and out through the outside of the pipe in a pipe. And it goes in and it cools all these surfaces, these shields in here, and it cools the vessel going down along the downcomer, which the scale you really can't see here, and goes down to the bottom and comes back up. All right, so that's the fuel salt loop. All right, the drain loop, as I said, these pumps pump the salt up into the bottom of the reactor vessel, go into the core, all right, and go up and over into the heat exchangers, up the riser, and in here, and any excess salt, there's an overflow line above the impeller that allows to flow down through an inside pipe of this pipe in a pipe into the drain tank. And these pumps also pull salt up into the pump intake as well. But any excess, again, flows down over the overflow into the drain tanks. In the top of the drain tanks, the flow that's coming down goes into a centrifugal separator, which helps separate out noble metals and gases and from the liquids, same as an oil separator does. Separates all those things, and that's for each of the 6 heat exchangers for that. The secondary salt, let's see, comes in through the pipes, through the outer pipes, goes down along the heat exchanger shell, again, cold salt on the outside, right? Goes down to the bottom and goes into the tubes, right? So it's into the twisted tubes, goes up the heat exchanger through the upper plenum, where it's collected outside. So the brown is the impeller housing, all right? So that's fuel salt inside the brown. And then the green is the secondary hot salt, all right? And that flows over the pipe in a pipe and goes over and goes around the outside of the tubes, goes down the tubes, and then goes over to the one end where the pump is and goes up into the pump, gets discharged and comes back through the pipe in a pipe in the outer shell. The saturated steam comes into containment, comes down the center of this heat exchanger, or cold gas, comes down to the bottom, turns around, and goes up through inside the tubes, comes up to an upper head where it's collected, and then one of the other pictures showed a separate nozzle coming out the top of the head and going outside of containment.
The refueling would be done in the drain tank below? Like
we separate refueling into fueling and defueling. We don't do both at the same time. It's not like solid fuel where you pull fuel out and you put new in. New fuel is fertile, is putting in every day, every shift, about 1 kilogram a shift is put in, and fuel is not taken out for 40 to 60 years. It just builds up in the drain tank. Whatever you add builds up in the drain tank. So the drain tank has extra capacity to absorb what fuel you have to add. The reason why you add fuel is because you fission material out. So you're adding fertile fuel at the same rate as you fission the fissile fuel. And then it's converted into fissile and fissions. Right? So we don't take fuel out routinely. This is part of the proliferation and safeguards issue. If you're not taking fuel out, then nobody's worrying about counting the number of atoms. Right? You're just leaving it in there for 40 to 60 years. So it's sealed for 40 to 60 years. It's not sealed for a year and a half, like light water reactors. It's sealed for 40 to 60 years. And that's except for maybe when you have to replace the lower reactor vessel, but that's intended to stay in the drain tank.
We need to come closer our second guest has also.
Okay. So this is a picture of just a small one if you wanted to put one on a ship, which I'll just breeze through. I already talked about how decay heat. The only thing I didn't talk about is you can see the red piece on the end there. That's a heat pipe heat exchanger. The lower part is in the salt tank, picks up heat, and the heat pipes carry the heat to the top, which in the top you see the two nozzles there. That's air going in and air going out. So it dumps decay heat to air through a heat pipe heat exchanger. I don't need to do power conversion. I think everybody knows that. Applications. We intend to essentially be a heat source. Whether somebody wants to make electricity or something else is kind of up to them. We want the stuff beyond the steam supply to be not safety rated. So you can do anything with it you want. You can build a standard coal plant, power plant if you want, but you can also do syn fuel or synthetic fertilizer, NH3, by mixing hydrogen out of the sea with either CO2 or nitrogen out of the air. The water that's cooling the reactor is the water that goes through to pull out the hydrogen and the CO2. All right, and you also can pull out the uranium out of the seawater in the same the same process. So the high volume, you're double using the pumping of cooling the reactor in that particular case, with the pulling out of the CO2 and the hydrogen. You can make the carbon dioxide and carbon composites and plastics for a net negative. Syn fuel is a net zero process. You can use it for district heating. You can make concrete or steel with thermal boosters or hydrogen electric arc heating or direct propulsion. This is just a quick example of the synthetic fuel production using the sulfur iodide process. In the graph on the lower right, you notice at 700 C, the black line, at 1 bar, you're about 60% efficient. And if at pulling it out, and that's better than electrolysis. But if you go to 900 C, which is our goal, you're nearly 90% efficient at pulling the hydrogen out. So there's desire to do that. Our view is we would put the reactors on a floating island in the ocean as submerged sea anchors to hold it in place and stable, and then build the seawater CO2 extraction, hydrogen extraction, and synthetic fuel production on the surface where the people would be to run that system, and hopefully get the oil companies involved in doing that and the distribution. But it'd be like a gas station in the middle of the ocean, or an massive oil well in the middle of the ocean.
Decarbonizing the ocean through nuclear.
Right. Synthetic fuel doesn't decarbonize it, but it prevents the carbon put in by fossils and not removed. So it's net zero, but it removes the carbon from fossil fuels being made into gasoline, diesel, and jet fuel in that sense.
So it's a different source. It's a source from the environment instead of pumping it on land. Okay, perfect.
Okay. So I guess let's go on to the next speaker. This is basically the politics that we were trying to solve in there. Liquid fuel is 10 times cheaper, consumes spent fuel and plutonium, denature weapons grade fuel. The fuel is locked up for 40 years. We recycle the zirconium for light water reactors. Low pressure and keep it simple. Passive decay heat removal, so the power systems are not part of the safety case. And change the 85-15 balance of plant to nuclear steam supply cost ratios. You need to get rid of the balance of plant cost in order to you can't just get rid of the nuclear plant costs. So that's all that had. That was the end. So thank you very much for your questions. I certainly appreciate it. I love answering questions.
It was a pleasure to having you. Thank you for being here.
You're very welcome.
Thank you. And I hope we'll speak soon.
Certainly.
Okay. my next guest is Jim Kennedy. He's known for mostly where I know him from the consultancy he's doing in rare earth elements, and I'm I always get a lot of questions about rare earths because there are lots of them, and today we get an opportunity to ask a specialist. So I will see if I can disconnect um, Phil from presenting. Let's see. And stop. Yes. Okay. Jim,
Yep, right here.
you're up. The presentation stopped. So, welcome.
Well, thank you for having me. It's kind of tough going behind Ed there. It's my topic seems maybe a little bit less exciting, but I want to expand on something that Ed was referring to there at the end. The problems for nuclear in general and rare earths basically are political problems, and political problems reflect political objectives, not safety concerns. So this is, the same problems that Ed and other people in this space are facing is also the primary driver behind the crisis in rare earths. I sent you a little file, so I don't know if you can pop that open for me. But
let's see.
I think your viewers, yeah.
And let's see. Oh, I have to connect this one. And share. And yes. Oh, no, now it's sharing the wrong tab. No, thank you.
Yeah, that's not it. But
stop presenting. No, it's mixing up my tabs. I don't know why, but PowerPoint presentation. Here you go. Okay.
All right. Okay, so what I did was I just grabbed some notes, threw some things together, and provided some slides. But the bottom line here is that the entire rare earth crisis for the non-Chinese world stems from regulations specific to source material. And of course, source material is uranium, thorium, or plutonium. And so what happened in 1980 was the US and the IAEA collaborated on redefining the threshold for source material. And when you parse out the definition, what it effectively did was label all rare earth byproducts as source material because of the companion elements, uranium and thorium.
Really?
The consequence was that the producers, the producers, what people don't know, they always hear about Mountain Pass or whatever. And they're led to believe that Mountain Pass was this great resource that supplied the whole world rare earths. And that is untrue. Mountain Pass is a resource that supplied lanthanum to the petroleum industry and then sold off the trivial amounts of other rare earths to whoever would buy them. The technology metals for the industry up until 1980 came from byproducts from the slide you've just brought up. If you look at the three colors there, there's China in green, the red is Mountain Pass, and the yellow at the bottom is monazites or other thorium, uranium bearing byproducts. And if you look at the point at which China essentially takes over, this is shortly after 1980, when the monazite producers find out that they don't have customers for this byproduct anymore, because when the customers would refine out the rare earths, they'd end up with a handful of thorium and then find out that they are a source material producer. And so what happened is the monazite markets and the byproduct markets dried up, which left just Molycorp selling primarily cerium and lanthanum and a few other rare earths. And China, of course, is an observer of the IEAE and is free to exploit great resources. So if you go to the next slide, I'll show you how this played out in the real world.
This one?
Can you do that, or do I control the slides?
No. You want this one?
Anyway, yeah, most people don't. Okay, that, let's see. Can you go up one?
Yes. This one.
Okay, most people don't know that, that thorium is, thorium and uranium are always associated with super high value heavy rare earths. If you try to avoid these two, what you end up with is very low value deposits. And if you can go down to the next slide, we can see what that looks like.
The properties of non.
So if you look at the bars there, that top line represents what comes out of China. This is the average production of their heavy rare earth and their light rare earth. And if you look closely, about 70% of what China mines has a negative economic value. So that green, that blue, that pink, that gray, that first yellow, those are elements corresponding to the table below that sell below their actual production cost. If you go down to Mountain Pass at the bottom, over 83% of what they produce has a negative economic value. And because it's a light rare earth deposit, it doesn't have recoverable levels of the heavy rare earths like terbium and dysprosium. So go down to the next slide and we're going to look at how this plays out in the real world. So here we have Mountain Pass on the far left. And this is times 100 kilograms, by the way. So in theory, Mountain Pass has about $1.30 in measurable economic return versus all of the rare earths that have a negative value. And if you go to China, it's, $16, right? So who in their right mind can believe that a company like Mountain Pass is going to compete with China in the long run? There's a very tiny margin there. So any shift in pricing and Molycorp turns negative, or MP Mine now. And what's most unfortunate is the Pentagon has bet everything once again on this two-time loser. And this is the mine that they're counting on to deliver, the U.S. Western economic and national security needs. Well, MP can't even produce half the rare earths, and what they produce generates tremendous losses, and just not very exciting. So that's interesting today, but if you look right in the center, there's something called phosphates and Fe apatite. These are the resources that the Western governments are, the mining companies in all US and IAEA compliant governments intentionally throw away to avoid potential liabilities associated with source material. So if you look at the relative values,
the ferroapatite, the metals.
Yeah, this is just like iron ore mines that have a phosphate byproduct that they intentionally pull out and throw away. This is something that has no cost. It's a waste byproduct of purifying their iron ore. They throw it away, but they throw it away because, well, there could be a liability built into it in terms of concentrating mostly thorium or uranium as you extract the rare earths. The other one is phosphate, like fertilizer. And in the United States alone, there's 6 phosphate producers that combined throw away enough rare earths to meet 85% of global demand. Now,
That's a lot.
there's no direct mining costs. Yeah, well, the entire non-Chinese world only consumes 40%. So if you did this, what you would be doing is dumping low-cost rare earths on China. How would they like that? That would be fun. But unfortunately, because of liability concerns, compliance concerns, the reputations of these companies dealing in actinides, they dispose of this stuff. They just literally throw it away. We work with I will just say, we work with one of the companies, but they, I think, speak pretty much for the rest of them. They would love to find a way to transfer the rare earths into a value chain and to rid themselves of the actinide liabilities. And of course, John Kutch and I and all of the members of the Thorium Energy Alliance, we've spent 12 years trying to convince Congress and the last 2 administrations to allow this. And, you know, with some success, there's a House bill and there's a Senate bill. But at the end of the day, every day, the guys from Mountain Pass or Linus run to a member of Congress and scare them, or, you know, they essentially argue away bringing these no-cost resources into the value chain, because obviously it would affect price. So to preserve the Mountain Pass, MP Mine, Linus companies of the world, the U.S. and Europe, all of our economic partners, Japan, Korea, were foregoing a guaranteed solution to the rare earth crisis, so that these publicly traded companies can feel secure in their profitability. And why does this matter on this video call, right? Well, who cares about rare earths on this call? You guys are trying to answer a bigger issue, which is energy. Well, lo and behold, what happens when you allow those 2 producers in the middle to start sending rare earths into a system that utilizes the rare earths and strips out the actinides? Well, what happens is you end up producing a tremendous amount of thorium and a quite substantial amount of uranium that would be available to fuel a modern nuclear economy. If the U.S. and the West, Japan, Korea, the EU, all of our friends and neighbors collectively worked on and solved this problem as proposed in the legislation, you would produce enough thorium, no cost thorium, as a byproduct of a no direct mining cost rare earth to pretty much fuel the entire planet. So, the next time somebody gets on their environmental high horse and tells you about, sustainability or, proper utilization of resources, you can just tell them, hey, today we throw away enough rare earths to pretty much meet the world's demand. And as a secondary or tertiary opportunity, there's enough thorium and uranium to also power the world. So this is the definition of sustainability, but in Washington, D.C., they prefer more solar cells and wind turbines. But anyway, I think these files will be interesting and available to you. And I'm happy to discuss more issues with it. Let me see what the next slide is. I can't even remember. I put those together late last night. Oh, oh yeah, the fun part of the story. So while we were asleep, if you look at this, this is a very incomplete list of what China started doing right around 1980 when the US and the IAEA regulated against our own interest. And it's a story about China building the equivalent of 5 national labs for rare earths only, exclusively. You look at that on a relative basis, the US has 1 national lab that does rare earths like part-time. Like that's a generous. And their focus is mostly political. So what happens is they're laundering government money on projects like rare earths from coal, because we want coal to be king again. So while China has pragmatic approach to the future and material science, we're literally operating in a dark, musty closet, serving political functions like promoting coal, rare earth extraction. So it's very, very painful for me and John, and I can see Kim's on the line. A lot of us have spent tremendous energy trying to solve this problem. Let's look at the next slide. Again, while the world slept, this is the number of rare earth patents filed by, the US, Japan, Korea, EU, rest of world versus China. Now I screwed this up a little bit. In the back row is China. And if you look, the first little red things are 000. That's because China filed its first patent in 1983. And today, China files more patents every year than the rest of the world combined. And by next year, by the end of next year, 2022, China will have more rare earth patents filed than the entire world collectively combined. So every rare earth patent for the entire world filed will be it will be in the shadow of what China has done since 1983. So when your governments tell you they're working on a problem, they're not. Like I said with my opening statement, regulations reflect political objectives, and political objectives rarely reflect public needs or safety. Anyway, next slide, let's see. So this is what it looks like in real terms. The light green is China's rare earth production. The blue is all of the low value producers like Mali, MP Mine, and Linus. And then that light blue is people that are producing from high value resources. And as you can see from 1980, they dropped down to a very, very low level. And in 2010, they started increasing again. And these are all non-IAEA compliant countries. So these are countries in Asia or Africa or in India that are smuggling these materials into China. So all of this, all of these colors here only reflect the resource. But keep in mind, mined rare earths, rare earth oxides, separated rare earth oxides have no meaningful use in the world. They're basically like yeast. You know, what are you going to do? You're going to eat it? No. You need to make bread. You need to make beer. So what happens is, this is the picture of the resource producers, but China actually has moved its monopoly from mining to controlling base rare earth metals. And this is an indisputable fact, which people get very upset about. China is the sole producer of new rare earth metals in the world. So if you want to make a rare earth alloy, or you want to make a rare earth magnet, or you need rare earth metal, the only new metal produced from virgin oxides comes from China. This is where their monopoly is. And so what China, they're so clever, they're now promoting and helping Asian and African producers get going to start mining, so that China can now get the resources from these other low-cost producers. You know, it's clever. Preserve your own resources. Quit making a mess in your own backyard. The problem is, the Pentagon is actually spending hundreds of millions of dollars promoting Western mines that exclusively supply China's monopoly. So anyway, that's enough on that slide. By the way, the red bar is China. The red bar is China's patents versus the rest of the world. Okay, why does it matter? The red lines show you where rare earths go. They pretty much go into everything. And if you're familiar with China's 2025 program, what China's able to do, since they control metals and the production of alloys and magnets, is that they can force every technology company in the world to move their commercial production inside China, and then China essentially can knock it off and incorporate these advancements into their 2025 program. So China uses this tiny fulcrum of rare earths and the leverage of technology to strip the world of its IP and its manufacturing. And for 25 years, Western governments have ignored this because multinationals were making money offshoring their manufacturing. So anyway, next slide. So pretty straightforward. The entire loss of the rare earth industry was the result of this 1980 regulation. The Thorium Energy Alliance and its active members have spent 12 years trying to solve this problem. We do have a bill in the United States Senate authored by Marco Rubio. The bill number is S2093. We have a bill in the House authored by Congressman Tipton, HR 4410. These bills are generally overlooked and not considered because the quote unquote rare earth mining lobby aggressively denounces the structure because they don't want these no cost, high value resources brought onto the market to compete with their marginal resources. So anyway, I think that's the presentation for me, and I'm open for question. I think the next slide just references an article on the sad linkage between this 1980 regulation, well, regulations in general, and lost opportunities as it relates to rare earths and nuclear energy. But so I can just answer questions because this is really just the backstory to what Ed was talking about. This is just the resources and the opportunity. So anybody's free to ask me anything.
Well, I can perhaps pass a remark. Wow, I thought we had problems here in
Oh man, it's so much worse. John Kutch and I have been behind the curtain so long, we've seen things nobody should see.
Well, then we are happy that we can talk to you here on this open channel.
Yeah, it is.
Yes.
There is a new process which my guest of last meetup did his thesis on. That was Diane Kemp with plasma separation of the metals.
Plasma treatment of monazite.
I'm very interested in low energy, low cost digestion, extraction for monazite. We're always looking for something better. If you've got something, I'd love to talk with you offline on that. But John and I and some other folks are doing a lot of laboratory work right now, specific to the bifurcation of phosphates and rare earths in a regular process. And there are some monazite issues that we're trying to deal with. Love to get your insights.
Gladly. Hulmo's got my email and I've got you on LinkedIn. I'll send you a message there.
Excellent.
Okay, I had a question about the. I was very surprised to see how much China is doing research on this. Are we really collectively, the rest of the world, just forgetting about doing research, or is this intentionally? Is there a lobby, or is this? Why are we not protecting this? I just don't get it.
Short answer is, as manufacturing consolidates in an area, it just becomes a fertile petri dish, and it generates new research, right? So if you build an entire city that does nothing but rare earths and then rare earth applications, all the new research and the drivers behind it are going to concentrate around that. And the only fertile petri dish of industry in the world is China, because the Europeans and the Americans were bamboozled by Friedmanite ideology that they could deindustrialize and live off of I don't know what their good looks and a service economy. So what happened is we live in fairly sterile environments with very low technological demands because we let China do it all. That's the short answer.
Just and they figure it out. It's
Yeah. Jim, so you're saying that Milt Friedman thought the West could get by flipping burgers for each other while China makes all the manufactured goods. How do we pay for them?
Well, yes. Well, you and me get to flip the burgers while, Milton Friedman's clientele, which are the billionaires, would essentially, live well on an extractive economy as they sell off legacy capital, IP, and et cetera. So he's talking about two different things instead of an us and them. But No, this is the problem. Even the Pentagon itself, through a series of administrations, moved away from independence to interdependence. There was a time when the Pentagon had to have U.S.-based technology and suppliers exclusively. Today, every component, the reliance on non-U.S. producers is shocking. And what the Pentagon does is it creates paper trails of plausible deniability so that technology metals can be ushered into the U.S. and converted from base metals to alloys, it's just layers and layers of deceit and disconnection from the industrial base. This is it's. I would say this after studying this issue for 12 years. You can't blame China for anything we've done to ourselves. And almost everything we've done, we did to ourselves. I read 35 years of summary research papers on rare earths from Ames Laboratory and a couple of other facilities that covered rare earths. I literally read every publication for 35, almost 40 years, and you could see there were literally in print decisions by the US, by the EU, or by Japan to transfer technologies to China, to offshore environmental concerns, to lower costs, for some other short-term advantage. So, this was all, we did it to ourselves, and China understood this better than we did, and that's reflected in their commitment to basic science, R&D, patent research. I mean, that graphic I gave you guys should be the most embarrassing graph in America, but I could only get about 3 publications in the US to print it because of people don't even understand why R&D is important. Anyway, we can do a lot of preaching on this, but if you guys have technical questions, anything non-political, I'll do that. I'll do political forever, but we may lose a lot of people. So any other questions?
Yeah, Jim. I just posted something. I reworded what Dion Camp had a question about. It's regarding, is it legal to internationally ship apatites that may be laced with actinides? So it's not. I don't think Florida Phosphate Company that you are collaborating with, they don't want to ship their actinide and rare earth laced phosphonogypsum out of the U.S. because of the
Kim, let me jump in.
Yeah.
The problem, as you and I know, is severe. They God, I don't know how broad the audience is for this, but let's put it this way. Any rational person producing high-value rare earths with actinide content would rather give those resources away for free as a mechanism for removing the liability. Nobody cares about selling it. Nobody cares about the profit. All they want is a rational way to dispose of the liability. And the Rubio-Tipton bill provides exactly that functionality. It allows them to on-site transfer their effluent, basically their phosphoric liquor, where all the materials can be stripped out and captured, and ownership and liability is bifurcated. It can never roll back on them. They get back clean phos liquors, they make a better product, and they never ever have to worry about what happens to the other stuff. They're happy to do that. The problem is they need a mechanism to provide a shield of liability. And for everybody on this call, how this relates back to what Ed's trying to do and so many other people are trying to do. The piece of legislation also creates something we call a thorium bank. And the thorium bank would be a multinational funding and development platform for any thorium-based energy system, because you don't want to keep storing thorium forever. You need to use it, and the only way to use it as fast as you'll acquire it is to burn it. So the rare earth cooperative solves the rare earth problem, and the thorium bank is a multinational funding platform. And for people that see the regulatory boogeyman everywhere, I can assure you the way this platform is designed, you as a potential developer end up in the driver's seat from a regulatory standpoint, because you would end up with sovereign partners, you would end up with sovereign fund partners, and you would eventually end up with the users and consumers of energy as owners. And because you have a multi-sovereign platform, you would essentially shop around for the best regulatory environment. And once one accepted, they would all wish they did. And then if one had internal political pressure to change it, the next one would jump in because the advantages are way too high. So what we designed is actually a very high scale architecture for solving the regulatory loopholes in an environment where multinational corporations have disproportionate control over governments, thus regulation.
Jim, I had another question about the politics of Brazil. Remember when Senor Batista was more than happy to send hundreds of millions of dollars to help fund the thorium bank and rare earth separation, because Brazil is burdened with tons of thorium in all their phosphates and beach sands, and when they mine niobium, it's loaded with thorium. And but even at the time, 10 years ago, when you were first speaking to Mr. Batista, it was like pushing 90.
Yes.
Under Bolsonaro, I don't think Bolsonaro has enough brains to understand supply chains.
Well, so Kim, we're back on that painful subject
of politics.
Cultural decline. A man like Elias Batista was the equivalent of like Benjamin Franklin and Bill Gates. I mean, he converted the entire economy. He swung Brazil from being a ridiculous third world economy.
Before Eliezer, there were no railroads or deep water ports.
No, he was a great and brilliant man, and in the world of, let's call it a brick and mortar, there's very few women that want to commit anything, because there's an alternate economy, the ethereal digital economy, where you put up a little bit of money, you don't hire many people, and you leverage it off of views or hits or whatever you call it. And you can, the return on de minimis capital in the ethereal digital economy is infinite. And that's why, some of the people that are working on this thorium issue and thorium energy, this is why you keep hitting a brick wall. Why would somebody bet against regulations and bet against, a 30-year cycle of getting something approved, when they could just jumpstart some silly, idea that gets digitized? And so what happens is the real world economy is having trouble competing against the virtual world, and that's unfortunate. And these, of course, Kim, Ed, everybody. I mean, these are the things you're overlooking in your quest to do the right thing. The right thing is a scale, a balanced scale in the virtual economies and the zero interest rate, ethereal bullshit investing with infinite zero risk returns always wins against real ideas. I mean, this is the
industrial
problem.
ideas, you need industrial ideas to feed people and warm houses and to create metals from oxides and halides. You have to have.
Yeah, but Kim, they are faking that right now with finance schemes around solar, right? I mean, that's part of the infinite digital ethereal economy where you're essentially promoting solar systems to solve an energy crisis that are built on large financial schemes. So we got to get off that subject. Yeah. We all know it. We all feel it. The thing is, what John and I and all the good folks from the Thorium Energy Alliance have contributed a lot of energy to is that we can offer the U.S. and all of its allied economies, Japan, Korea, EU, Canada, we can guarantee them uninterruptible, low-cost rare earth resources, and in exchange, give us a development and funding platform to solve the world's energy problems. And to support that, all you need to do is communicate to your senator or your congressman that there's some crazy bill in the House or the Senate called a rare earth cooperative bill. If you want to help, don't talk about nuclear, though, because they're scared to death of it. You just talk about solving the rare earth problem, and hopefully we can get there. Yeah. I don't want to cast shade on people, but I know some super dedicated people that have committed tremendous amount of time to solving this problem, and funding is always the problem. And then you can look at some straw man savior like Bill Gates, who's trying to fund new nuclear with government money and Chinese money. What does that tell you? He doesn't even believe in it. He's got to put somebody else's money in it. He could cash roll it himself. So the only way around
he has $50 billion in the bank. Yeah.
Right. But he's not doing it. He's in line for free money from the government. What does that tell you?
Well, the free money from the government will never be forthcoming. If it forthcomes from China, they'll capture it.
Well, at the end, China will have it all. So anyway, I'm getting kind of preachy here, but at the end of the day, we believe we have a platform that can't be flanked. The platform we have can't be flanked because it has a single mission, and the mission is tied to the equity owners, which would be the EU, sovereign funds, and then ultimately end users of energy and consumers. But all of this stuff ties back to a simple 1980 regulation, and all the solutions are quite simple. Anyway, so that's it. I didn't want to get political. I didn't want to get economic too much, but if there's any more baseline questions or whatever, happy to answer anything.
I have an observation.
Kim, let him go first, okay?
Yeah. Go ahead.
My suggestion is I am researching the past 6 months a multi-stakeholder collaboration systems, because connecting people is one of the most difficult things in this kind of areas, because everyone is afraid the other one knows something I don't, and the other way around. So the thing I really learned is we're all like 13, 14. We're behaving like we're so the mindset we're taking is like he's got a bigger one than mine. Oh, I don't want to do the work. I'll give it away. And that's the problem of today. It's like it's this country against that country, and you
Right.
don't want to do the work. You just give it to someone else, even if it makes you vulnerable. You don't care, and that's really wrong.
So this multi-stakeholder thing, you're onto something. John and I spent a lot of time on that. So I there's a Greek reference in my head that you should all have figured out, and I won't say it out loud. But the strategy here is very similar. And what you do is you play on the demonstrated global concern for secure access to rare earth resources, right? That's what you're selling. And it's not me. I'm not the one doing this, but there's a certain amount of fear associated with that, concerns, national security concerns, concerns for technology corporations to control their IP. So the driver for solving the rare earth issue has a self-laced component of fear, and that's a driver. And so when you present all of the players a guaranteed solution, and the guaranteed solution in the legal form of a cooperative provides them direct, unlimited access at cost, right? So there's no profiteering in the middle.
Exactly.
So the resources you get cheap, all the savings get rolled into the end users who build factories in Korea or Japan or the US or wherever they want to build them. The point is they have control over their destiny. They're getting it at cost. So that's the fear alleviator, uninterruptible, high quality, and at cost. So you resolve that fear for them. In exchange, they're going to give you this platform, and the platform gets sold on the exact same basis, but instead of selling it to Toshiba, you're going to be selling it to NATO, the North Atlantic Treaty Organization. And you're going to say to them, here is a legitimate risk and concern, and there needs to be some collaboration in building the foundation. And I want you guys to just think about that. That's a pretty easy sell. And once you get a buy-in at that level, you're done. You're done. Because once you get that buy-in, when you go on the commercial side or the sovereign investor side, they already see the governments are committed. And you have to be very generous. You have to guarantee the contributing governments top line revenue in perpetuity to offset the tax losses they get from corporations that don't pay taxes anymore. You see? This is a very, very detailed architecture, but it's very, very durable. So they're bought in. They're in the game. The thing starts forming. China comes up with the reactor first, but these guys are all desperate to be locked into something that gives them revenue. So guess what? Maybe they resist it. So you just solved one of the single biggest problems in the world. This is very, very complicated architecture, and very few people I've never talked about it publicly like this before. We try to keep it that side of it minimized because someone will try to find a way to exploit and demonize it. But this is what you need. You need multi-jurisdictional buy-in because China has a 10-year head start.
It's almost like you need a decentralized body of autonomy which will give trust between parties which don't trust each other. And
Well, the decentralized entity is the bank, and the bank is going to be owned by the contributors, but it's a private corporation. So what happens is it may be formed in the U.S., but it will align itself with the first place that gives it the best regulatory environment. So it may end up being a company that builds and designs reactors under the Canadian flag because they're very rational, right? And if the U.S. pushes Canada like they did with the CANDU reactor, you just move over to South Africa because their needs are greater than anyone, right? So this thing is super autonomous and super flexible. It can move. And once they figure out it can move, then they get scared not of it, they get scared of losing it. So what happens is you'll end up with a very, very secure regulatory patron, right? They're going to make sure. So anyway, like I said, this architecture John and I developed took a long time to put together. But when we designed it, we were also thinking that in the world we live in today, you have legacy energy producers that have the power to enlist the State Department and the U.S. Army to basically grab somebody else's resources, right? So those are the same people that can do anything to anyone. So that's the level of stability and security we built into it.
Well, everyone agrees here that the poor actinide elements have been severely uber-regulated. All right. Well, one thing that's very key to molten salt chemistry, and particularly if you want better efficiency, is the beryllium supply chain has been perverted by the company that was once called Brush-Wellman, and now they're Materion. But the guy that spoke to our Thorium Energy Alliance, back in 2012, and he's a guy from Venezuela, Edgar Vidal. Remember Edgar Vidal? Well, he had to leave that poorly managed company, Materion, and he's now doing like niobium or some other alloys like that. And but that's crazy. Materion keeps uber regulating, ratcheting the regulations of beryllium like one or by an order of magnitude every 5 years, because they don't want anyone to be able to afford the equipment to like even look at even put your hands on an ingot of beryllium or any beryllium compound. And I think the thorium bank can bust.
Yeah, back to my opening statement.
Yeah.
Regulations reflect political objectives, right? Political objectives are driven by money. Money comes from contributors. We call them campaign donors in the US, but it's essentially bribes. So regulations reflect the interest of legacy assets, legacy capital. And so, yeah, we're trying to fight that. That's the biggest challenge everybody has in front of them. And the way to do that is to create an autonomous platform that is movable, right? That can drift with patronage, with shifts in patronage or pressure, and that's what we designed. All other alternatives essentially are waiting around for a government to provide regulatory passage. And at the end of the day, there's more money in legacy capital and protecting legacy systems than anyone on this call could ever muster, right? It obviously exceeds what Bill Gates is willing to put in, right? Think about that. Bill Gates. Yeah, so how do you do it? You need a collective vested interest that is not that's destiny is not affixed to a single sovereign. It's got flexibility, and that's what we designed.
So it's transportable to South Africa or to Brazil or wherever. We'll give it a regulatory
anywhere.
home for production.
Yep. Yeah, think about that. The NRC gets pressure from somebody. They start clamping down. You start talking more to Canada or to anybody else. Somebody somewhere is going to want this because they're going to negotiate the lion's share of manufacturing. They're probably going to try to argue a better cut at the guaranteed top line revenues. That's fine, whatever it takes to get it going. All other avenues lead to a dead end, right? All other avenues lead to the regulatory walls that are built by legacy capital.
Yeah.
That's very problematic. There are only one or two roads that actually lead to success, and those must be walked very carefully.
Yeah. Well,
Yeah. So
look.
you look at some people that are trying to get regulatory approval in fairly unstable governments, right? I'm not going to mention any names. Great ideas, good people, but they're essentially trying to develop a thorium technology in a sovereign system, which may be at flux and ultimately may subject to the pressure from a different government, right? So at the end of the day, as they're handing you a certificate of regulatory approval, a certain amount of State Department influence comes through. A Mike Pompeo shows up and starts telling you what and how you're going to do things, and that you just see that piece of paper get pulled back again. People, I don't think anyone can appreciate that the market for energy is so big that energy companies have embedded themselves in governments and can cause governments to declare war on countries that aren't threatening anyone.
Yeah, like
this happens
Iraq.
all the time. Libya, Syria. What is it all about? It's all about hydrocarbons. And those same people will reach into this, they won't use the same tools, but when they see this as a threat, they're going to respond in equal measure. And anybody who thinks that they want this to happen, they're going to allow it to happen casually, hasn't really thought through the pathology of money, right? The pathology of money is endless.
Oh, you mean the circuitous, by pathology, you mean the circuitous pathways that money can take?
No, pathology as in the disease.
Oh,
the disease.
Oh, like the General Electric type disease?
Yeah. So all morality set aside for money, right?
You know, DuPont and Dow are going the way of General Electric. It's so sad. Even the chemical industry in this país of ours is going the way of GE.
Right, but we also go ahead, Chris.
That disease is called greed. The name of the disease, greed.
Yes. It's blinding.
The name of the disease is greed.
And there's literally nothing in the world that can stop it. It's too powerful. So you have to outsmart it. And that's why we built an architecture where we could shift around. So when one sovereign support dries up, as political money flows to it, we could essentially just shift to another and stay alive. And in the end, you may end up with a country that doesn't really care to be in America, the U.S.'s favor, but you'll still have a regulatory platform and you'll have a demonstration reactor that you prove to the world this is the safest reactor in the world. Why does your government make you use less safe reactors? No matter what, you win if you can get to the point of a demonstration reactor on a reasonable scale. But that's a very, very tough road. And on that tough road, you still need a pathway that can essentially guarantee regulatory completion. Because even a demonstration reactor can end in a mothball. The molten salt reactor, the MSRE, is a case in point. Safest reactor ever invented at that time in history probably still, and it died. It died because Alvin Weinberg put safety first, right? So this is it. I love the mission. I know where we need to be. We just have to actually outsmart our adversaries, and to outsmart your adversaries, you have to plan in 3 dimensions. You know, you need to be able to be extremely flexible, and that's the strategy we created under the cover of solving a very serious and well accepted crisis, rare earths.
So the way to go is very slow, and first get the bills we need to Congress just to solve this first step to open the door for the second and the third.
Let me say this: if the law that we wrote was passed, the very next day you would start raising international money for a rare earth cooperative. You would have access. Our government would guarantee access to the highest levels of government and industry through the Department of Commerce, and it would also guarantee access through the Pentagon, the Defense Department, and NATO. So you would go out and pitch solving both of these problems at the same time. And once you were granted the authority, the rare earth cooperative would be generating hundreds of millions of dollars a year in uranium that it would sell into the energy industry to provide baseload funding for the thorium energy program. Any money it was able to extract from NATO partners and then sovereign investment funds and eventually end users would fund the entire rollout. So it wouldn't be slow, it would be very fast.
Yeah, faster than waiting for congressional approval for like funding. Remember the integral fast reactor or something? No, what was it? It was the fast metal liquid fueled reactor that Al Gore killed under.
Yeah, so you don't need any approval because you have your baseline funding.
Yeah.
And you start building it, and while you're building it, before you fuel it, you shop around for the regulatory environment that's going to be most conducive. And when you get that environment, and then you set up and fuel it and demonstrate it there, so you've lost no time. There's no waiting. The Canadian regulatory environment is wide open to any of this, right? The Canadian regulatory system is based on entirely different principles than most of the rest of the world. So there isn't a single obstacle in Canada for developing a demonstration reactor. And as you're developing it, you can be talking with regulators on everything you need to actually have it regulated. Let me tell you a little story. This is a story about me and John working in the United States Senate, meeting with Senator Harry Reid's office and meeting with, who's the other senior Republican? Anyway, we were meeting with the 2 most senior Republicans in the US Senate. We laid this entire thing out to them. And you know what they told us? Their senior staffers told us? You get multinational financial commitments, we'll let you write the regs for this entire technology. Because that's how it works in the US. The industry writes the regs. You guys know it's true.
I know. If you know the knowledge of a banker, I know a family of bankers. I had a discussion with them. They wanted to fund the first Gen 4 reactor in the Netherlands.
Yeah, so what? That's fine.
Money behind.
So what they're doing, though, they're walking into a snowstorm naked. We don't want to do that. We want regulatory authority, either from Congress or the president, to develop this platform. And the platform legally requires that we get multinational investor participants. And once we do that, then our legally sanctioned platform is mobile, right? You start building it in the Netherlands, and then somebody in the Netherlands gets influenced by somebody else who sees this as a risk, you know, you run into trouble. You don't want to be married to a single sovereign regulator. You need the flexibility, and so what you need is skin in the game, and you need to promise them top line revenues, so to replace their tax base. That none of them, you know, it's all shrinking. They're all fucking in Ireland, right? Or any other place that has no taxes. It's a scam, right? So these governments are supporting multinational companies that aren't supporting the host government. So you just commit it at that level, and then once they see revenues coming from this, they'll defend it. But if you're just a bunch of bankers in the Netherlands, you're going to set up shop in one place, and if it gets killed there, you're dead. And anybody else who's looking at developing it, look, there's a bigger problem, guys. This is the single biggest problem literally no one can get their head around. China has a 10-year head start. Once China develops its commercial reactor, they are going to give the reactors away for free. Yep. I swear to you.
But it will come
give the reactors away for free. They'll give free fuel. Right, free fuel. And what they'll say is, you need to pay us 2 cents per water. You need to pay us X per joule, right? And what they'll do is they'll give these to every country in the world, and every country in the world will essentially be paying them a tax. And it will be the first global empire to exist on our planet, because they will have distributed the power systems to every country in the world and be getting a tax back from it. So Elon Musk can't build a cheaper reactor than a free reactor, right? Bill Gates can't. The bankers in the Netherlands can't. The only way to solve the problem is to lock in multi-jurisdictional players and promise them online revenues, because when that China reactor shows up, they need a reason to say no. This is how far down the road I've walked this thing. I've walked it a lot further than this.
Hey, Jim, if we continue procrastinating, and we don't have if we don't have any cooperative, any co-op, at least on paper, then China wins, because they'll send military bases manning the MSRs with Chinese technicians, and they'll just and then they'll pay China for the electricity. Americans will pay Chinese, pay the government of China for power, right? And and it'll probably be competitive with California price power, undoubtedly. What do you think? What do you say? Are you there?
I think his internet connection just went.
Oh, his connection is lagging. But I was saying, Jim, if Sino MSR bases are set up throughout the West, nobody in the West, just like Brazil won't let China in their niobium factories, China won't let Americans or any non-Chinese into their MSR sites, right?
Yes or no, doesn't matter. At the end of the day, they're going to have some remote system that essentially will denature the entire system, right?
Yeah.
They're going to build that in, because they're going to say, well, if you're not paying us our 2 cents per kilowatt, we need a way to turn it off. They're going to have that power.
Yeah,
and
because
that power is going to be built into that thing hard.
They'll supply all the salts. They'll just have some poison tank that will just kill it.
Right, of course they will. And look, this is all, it doesn't matter, because they already won. Once we're using their energy, we're paying them a tax. They've won. And look, going down this road, I've been down the road, if there was a flat earth, I walked off it and I'm halfway to the moon.
This is why
contingencies, Jim, and at the end of the day, commercial reactors they give away for free. They're free.
Well, hey Jim, this is why relying on IP, intellectual property, as a source of revenue is just like poor Sorensen and David are relying, is not going to get you anywhere because of China.
Right, because at the end of the day, you won't have a sovereign to support you. The money won't be there, or the bankers behind it will see more money transferring it to China. China ends up with all the IP anyway. We all lose again. This Milton Friedman legacy of selling off, shorting the future, right, for a pocket full of money today. It's been destructive, and it's the controlling machinery of all Western governments. And the only way to solve it is to build something that's multi-jurisdictional, mission-based, and then therefore can't be corrupted. Everything else is corruptible.
Yeah, Milton Friedman has corrupted all his false teachings have corrupted even 3M.
Guys, I'm sorry if you keep hearing references to Milton Friedman, but
I've worked at, they've been
I've written a couple papers on this.
He's well known also outside of the U.S.
Hey, Kim. Yes, I mean the guy. Anyway, listen, Kim, let some other folks ask a few questions because I actually have a call that is going to start in 6 minutes.
Okay.
Yeah.
Let's see.
Hay qualquer outras perguntas? Are there any other?
I can perhaps, Jeff, from the southern tip of Africa, make a few remarks. Jim, it sounds to me like you need to come visiting. We can offer you perhaps avenues out of your groove. From an outside view, and this is not a critical remark; it's a supportive remark. You seem to be stuck in a deep groove there in the American politics and those things. Remember, we come from a world where we are basically patent crackers par excellence in historically. We know how to get technologies done around and through patents. Patent is only as good as the money that protects it.
Yep.
Academically, it's worthless. And to find ways through and around patents. So the fact that China has been producing, they're at the peak 10,000 patents is bloody good news for guys like us, because it's a wealth of information that can accelerate any technology-driven program. Then secondly, we are passionate about Africa's future. I was standing in Shanghai at the Chinese Minerals Conference a while ago, doing a presentation about, and Africa has got the potential if we can solve our own little political problems, which sounds like a mole's heap against your mountain. We've only got the greed on our side presents itself in the form of obvious corruption that you can see a mile away. I think the corruption in your system is much more elegant but it's still there. I mean, the human beast is the same. There's no difference.
It's still there. It's just not as obvious.
All racism is
bullshit.
It's a tool that's driven. I always say, if you want to start talking race, it's like choosing your beer on the shape of the bottle. You must choose your beer on the content of it. So if you associate with people along racial lines, you're choosing your beer by the shape of the bottle. In other words, you are making a serious mistake. Coming from that point, we do have elements in our system which are radically different from yours. So, as you know, innovation is done from different angles. So, and that's how you get out of groups. A third of this meeting were my either colleagues, ex-colleagues, or friends from the southern tip here. So we are silently very excited because, as you know, we've got control as a Thorium there are in our networks there are rare earth programs running where we are looking at beneficiating. Mineral beneficiation is a core strategy in Africa, and we are passionately part of that to establish full value chains in Africa based on Africa's mineral resources. That's the only way that Africa's poverty will be solved. We function, and our network stretches sub-Saharan Africa. You know, name it, Zimbabwe, Zambia, Tanzania, Malawi, Uganda, Kenya, DRC, Congo. I mean, we go up Nigeria. You know, our network stretches that far, and we are all passionate group of guys that are looking at mineral beneficiation in Africa, building the and of course the Chinese also knows that, so they're trying their best to get their hooks into the system here, but the both corrupt politicians have very close relationships. The man on the ground is not. I mean, there's a huge sitting between, and Africa has got the promise to be the next. The Chinese boom is going to be a mold in this place against the African boom that can potentially happen. I mean, Hulmo and I know the Thorium Alliance has been looking at the cryptocurrencies as a tool to further the and crypto is making technology good. When it comes to value transfer, in the sense of every African has got a cell phone. The banks are limited, cash flows are limited. So people jumping the banking technology to a large extent. Although the colonial has
Chris? Yes. I'm certain we could do an episode about this alone, this subject of funding it through a different means like cryptocurrencies or other means. We could do a whole episode only about that subject. I'm certain. But I like to ask you guys one thing. Jim, could you give me the email address of Ed? Because Deanne asked me if I could have your and his email address. So do I have your permission to share your email address?
Yeah, you can share it with anybody. That's fine.
Okay. And John.
I think John is already on the other call. I'm supposed to be on.
Yeah, it's time for Jim to go to the other call. No,
Okay.
Senor Kennedy?
Then I wish you a very good evening, day, morning. And thank you for
Yes, feel free to follow up with me privately on stuff. There really are some things I said that I usually don't say, but there's a lot more to this. And you know, we're at the point now whether you might as well throw it all out there, because we're crossing the tipping point where China ascension will be beyond reversal or containment. And all we've done is essentially, you know, backed ourselves into a corner, hoping that, you know, the fairy princess was going to come along and bless us. We're way past that. We need some aggressive action, but it has to be smart action. We can't waste resources going down a dead end. It needs to be a coordinated effort where we've anticipated all the roadblocks, and I'm happy to discuss at length everything John and I have learned in 12 years.
It was my very pleasure, and I will definitely get in touch with you.
All right, very good. Chris, great. Kim, great seeing you again.
Lovely. Thanks for meeting you. Them as well.
Thank you all. I gotta go.
Yeah, bye. Thanks a million, Jim.
Me too. Good evening, guys.
All right, Kim.
Bye-bye.
Thank you, Chris.
Pleasure.
Hello. Thank you, man.
Hey, Hulmo, I like your setup with Google Meet. Esta vez it's more stable, and you can see everybody and hear everything that's going on more.
Yeah.
Hey, we have una persona de Iran conozco with us.
An Iranian.
Surush, can you hear us, Surush?
Yeah.
Anyway, yeah, he's a nuclear engineer, originally from Iran, but now living in por la Francia.
Oh.
And France is
He doesn't
nearby
have a
you,
mic.
and France ain't too far away from you guys.
No, he's in Helsinki.
Oh, is he? Well,
Yeah.
last I saw, he was.
I will translate for him because he doesn't have a mic. So if he types, I will say it. He moves to Helsinki. So.
Oh! You moved to Helsinki. Hey, last time we talked, Surush, you were in Paris, Paris, no?
Let's see.
Oh, so you don't have a mic.
No, he doesn't have a mic. Correct. I remembered how it goes. Yes.
Anyway, yeah, you'll have to bring it. I'll just tell him you'll have to remember a mic next time we have a meetup.
You can also log in on your mobile phone through Meetup. So that's a
Yeah.
possibility. If you take the same website and link, you can also log in with your mobile phone. Then that makes it a lot easier.
Oh yeah, and this is Google Meet on your phone, especially if you have Android, is excelente, no?
Yes, definitely. It's Google working on Google.
Right. Now I remember, Homo, you're telling me that usted es puro argentino de descendencia, but by descendants. You're well, but where did your parents you don't necessarily look puro porteño. You don't look like you're from Buenos Aires because they look like Italiano.
No,
You know?
I'm like a mix of
Indio
my family
nati
is all over the world.
do you have a little bit of local indigenous Argentino indigeno in you?
Yeah, 1/8.
Yeah, and
So I've got the people
un
from
poquito de
France
africano.
moved to Argentina. The people from Germany moved to Argentina. The
Yeah,
Indians moved.
Argentina is a bigger melting pot than the U.S.
Yeah, it's like my family. I've got like a little bit Swedish, French,
Well,
German,
but
and a
your
little bit.
parents came over. Your parents came over con acento porteño, no?
Yeah, my mother comes from the Netherlands, and my father comes from South America and South
Oh, yeah,
Cambodia.
but
So
did you ever live in Argentina?
yeah, like she traveled through the world in the 60s and 70s.
Ah,
So
oh, that's how she got together with your papa.
yeah, exactly.
Well, I'm totally mixed up. I'm a quarta parte Dinamarquese, Noruega, Swiss Allemand, and then my English quarter